In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space.
That sounds like a conspiracy to me.
Globe proof.
Yeah, it's below
All
the
right.
earth.
Good evening, gentlemen.
Hello, hello.
All right, so tonight I was going to host, tonight I'm hosting an open discussion on ether dynamics, relativity theory, and interferometry, which is the best supporting evidence, in my opinion, that the Earth is stationary with respect to a dynamic ether wind. So this will kind of be an open format with guided discussion. So I wanted to kind of lay out my position and then lay out the relativist position. And then if anyone has any agreements or disagreements, I wanted to basically lay out the format for relativity theory and then go through and analyze some thought experiments, some paradoxes, and some measurements that are done that directly contradict the theory. So if there's anyone that supports relativity theory in the chat that wants to follow along or whatever, that would be really cool. So we could set up, our two paradigms, what we agree on, what we disagree on, because a lot of people have their own kind of custom interpretation of relativity theory and what they think it means. So I think it would be really important to start fresh, and then we could all see each other's positions and go from there, and then where we differ on interpretation, etc. So to lay that out, lay out the framework of interpretation, and then go over the experimental evidence that's put forward that supports the interpretation. All right. Any questions so far?
You're good to go, boss man.
Cool. Would anyone like to support relativity theory? No
Can I go
relativists?
against it?
No relativists in the chat? That's crazy.
Yo, is ether dynamics all one word?
Zanuck a DM or something?
Yeah.
I'm a relativist.
Okay. Witsit's going to be our relativist, and Shane's also going to be a relativist. Okay? Since no relativists showed up tonight. All right. So let me screen share here, and then we'll go over some basic definitions and lay out the framework of relativity theory, and then I'll lay out my framework.
I'm actually also driving, Shane, so I might need to pick up some slack here. I gotta run in the store real quick.
No worries. Okay.
I mean, I can be full blown annoying relativist, or do you want to good faith, intellectually honest relativist?
Put on your Glober glasses.
Good faith, intellectually honest relativist until you come to the realization that it's not going to go very well if you have morals.
And then immediately Professor Park's relativist, where you dig in super hard. Yeah.
So basically, the best their side has ever had.
Yeah.
Yes.
Yes.
Yeah, we got
Okay.
talking about the age of the Earth for some reason.
Actually, that's my first point. Actually,
Can you go full NASA chill on us?
nah, we'll still man them.
Word valid level relativity.
All right. So to start us off here, for my position, it will be a stationary Earth with respect to a dynamic ether. Any measurements of motion that are attributed to either Earth rotation or, I guess there's no other rotation to attribute it to. Anything that's attributed to Earth's motion would be explained by ether wind. With respect to a stationary Earth, the speed of light is measured as c equals c plus or minus v, v being the velocity of the observer. So Like any other wave, light will be measured relative to the velocity of the observer. Some physical properties of the ether would be the vacuum permeability and vacuum permeativity properties. And in the ether, simultaneous events will always be simultaneous, irrespective of the motion of the observers. And what that means is relative simultaneity will be an apparent effect. So, for instance, if you're moving towards something and you hear it first due to Doppler shifts, so you might perceive that it happened first, when in reality, the event happened simultaneous with respect to some other observer, meaning it truly happened simultaneous, and it's not going to lead to a physically different outcome. So that's my position. If there's any questions on that, we can answer those. If not, we'll get into the relativist position.
I'm good.
Okay, cool. So, and for the ether dynamic position, the lab frame, like the is an inertial frame defined as being truly stationary. So that's a distinction between the relativist position that's going to be coming up right here. So we'll go over the relativist position now for definitions of an inertial frame and what are the rules of relativity. So the first two postulates of relativity are that all inertial frames are equally valid, where the laws of mechanics hold good, so will these equations. And he defines an inertial frame as being in uniform rectilinear motion. So as long as you're traveling in a straight line at a constant speed, you're in a quote unquote inertial frame as defined by relativity. The second posti is that the speed of light is c irrespective of the motion of the source or the observer, meaning that how I was mentioning earlier that there would be a Doppler frequency shift in sound, and you could, tell a velocity difference from that. This theory is saying that there will be no shift like that in light, and it measures constant irrespective of your velocity. And in fact, if you're moving really, really fast, you'll experience length contraction and time dilation, which we'll get into here in a second. But more importantly, as a consequence of this theory, everything will be explained through frames of relative motion, and there won't be any need for fictitious frames to be invoked to explain electromagnetic processes in particular. And also, the split making time all relative to different scenarios that you're doing your analysis in, it's arbitrary. Time and space are not absolute, and because all inertial frames have to be equally valid, so must the sequence of events that occurs in them, and this will lead to the principle of relativity of simultaneity, which is different from the absolute simultaneity, where relative simultaneity is an apparent effect. In the relativist theory, relativity of simultaneity means that there's going to be a physically different outcome because the sequence of events also has to be valid in the frame. Otherwise, the frames are not all equal, and you're catering to a preferred frame, which would be like the stationary frame of reference that's going to perceive the simultaneous event. So in order for these frames to all be equivalent, you have to be able to use a transformation to basically change the order of events in both frames, or make them interchangeable so that you could change the outcome so that one frame receives the simultaneous event and one frame does not. And the only way that you could do that is if the sequence of events is equally valid, which would lead to physically different outcomes. So is that clear so far? Does anyone have any questions, and is there any relativists in the chat that have disagreements?
I have a question, Alan. So to go back to the invariants and C, which leads to issues with them, particularly where they had to invoke a length contraction relative to velocity itself. With the ether theory, I know Lorentz himself, when he first started out, he wanted to invoke contraction relative to ether, at least as there was something substantive there. And we know that the modern theory of ether is that it's not a stationary ether. With a dynamic ether, which velocities differs with altitude. How do you relate motion relative to that? Is that an issue? If not, if you can help me clarify how motion, particularly how you use it with GPS or anything else that you're going to cover. I don't want to go ahead too far, but how does that relate to um, comparing velocities to it?
Yeah, so the altitude difference from like, yeah, I am going to get into that, but to touch on it real quick, the altitude difference from the signal sent to received doesn't seem to matter that much in terms of the velocity gradient that was measured, going from Miller's data and Galev. And, we only have a limited amount of data on that, but there doesn't seem to be that big of a factor for it. But that's actually wrapped up in a GPS correction where they do what's called a Lorentz rotation, which we'll get into when we get into the GPS segment.
Cool.
Because they would attribute that correction to Earth movement, but as I said, I'm going to swoop up all measurements that are attributed to Earth movement as dynamic ether. So we'll definitely get in.
I didn't want to go too far ahead. I was just curious, but then I figured it was going to be part of it. Thanks.
Yeah, we'll definitely get into it. So to just kind of reiterate my interpretation of relativity and where everything that I presented as the Steelman of relativity comes from this. So this is Einstein's paper in 1905 on the electrodynamics of moving bodies, and what he was saying here about how tests and experiments that were done to test the velocity of Earth, had failed. So maybe such a light medium doesn't exist. And this is about, throwing out the medium because of the relative velocity measurements that weren't being made. Because through the history of interferometry that we'll go over a little bit as we continue, is they found that they could measure motion using interferometry. So they were like, okay, if we build a big enough interferometer, we can measure the motion of the Earth through the cosmos, because we're on the Copernican principle grind. So the Earth has to be moving at 30 kilometers a second. So they were going to try and substantiate that, and they were coming up with a bunch of quote unquote null results. So anyway, he's building upon these null results as an interpretation that the speed of light is the same in all reference frames when you're in uniform motion. So you can't use it to measure velocity. And then he'll actually later introduce link contraction and time dilation as we read on to really ensure the reason why you in fact can't measure that velocity change. So let's see here. Let's see. So this is where he makes those assertions here about the principle of relativity, which is that all inertial frames are equally valid. Where Newton's laws of mechanics hold good, so will his, and he defines the inertial frame as being in uniform motion at a constant velocity. And then we have him saying here that the speed of light is always propagated at empty space with the definite velocity of the emitting body. And he's saying that there will be no need for a luminiferous ether. So there will be no need for a physical medium for light to propagate in. It can just propagate in empty space. And there'll be no need to invoke an absolute stationary space, meaning a preferred reference frame or using something that all motion would be relative to derive an absolute velocity. And all velocities are relative to some other velocity. All motion is relative. And as he's going on to say, we won't assign velocity vectors to a point in empty space where electromagnetic processes took place. So again, just reiterating that everything will be explained within this theory, within the framework of relative frames. There won't have to be a preferred fictitious frame invoked that is used as absolute stationary space where you can make relative distance and time changes measurements with. So these are the explicit rules here. Any questions so far on that? Or any contentions?
I would say that's where the first magic trick comes in.
Yes, sir. Yes, sir. All right, so we'll continue on here. So we've got the definition of simultaneity here. So again, with this system of everything being relative and there is no absoluteness as a consequence of the two postulates, we have to redefine absolute simultaneity. And what we're going to do here is describe that as Einstein gives the example of suppose there's a train that arrives at 7 p.m. Every night for him. And when he looks at his wristwatch, as soon as that watch hand hits 7 p.m., boom, that train's there, right? But say somebody lives in, another time zone and their wristwatch is going to have a different reading for his simultaneous event of the watch hand and the train arriving. So he's saying that events are disconnected and they're only relative between these two observers, right? And based on velocity, time and space are going to change as a function of the square of the velocity over the speed of light squared. And that's going to be our link contraction and time dilation as we continue to read. But that's how he's redefining simultaneity. And he goes on to say here, we shall not discuss here the inexactitude which lurks in the concepts of simultaneity of two events at approximately the same place, which can only be removed by abstraction. So in other words, if you're presented with a scenario where it's obvious that both frames agree on the simultaneous event, like the physical outcome, agrees with the stationary frame, then obviously time and space are absolute and none of this is real. And he's like, we can only really remove this with abstraction, which we'll get into the abstractions as we continue. So any questions or anything? All right, cool. Right before we move on, we have here. So we see that we cannot attach any absolute significance to the concept of simultaneity, but that which two events which are viewed from a system of coordinates are simultaneous can no longer be looked upon as simultaneous event with envisaged from the system which is in motion relatively to that system. So distinctly physical different outcomes due to this. All right. And I think that's about it for that. We get into some equations here. Oh, yeah, this is extremely important. So we talked earlier about where these equations apply. Oh, one sec. So we talked about where these equations apply. And we have the inertial frames defined as being in uniform rectilinear motion, so just in a straight line at a constant speed. But he also says here, he gives the example that his equations also apply when you're in rotation. He says, and if a clock at A is moved with a velocity nu along the line AB to B, then on its arrival at B, the two clocks are no longer synchronized, but the clock moved from A to B lags behind the other, which has remained at B by 1/2 t nu squared over c squared, t being the time occupied by the journey from A to B. So he's applying his equations here, and he's going to go on to say that it is at once apparent that the results still hold good if the clock moves from A to B in any polygonal line, and also when points A and B coincide. If we assume that the results proved for a polygonal line are also valid, they're also valid for a continuously curved line. And we arrive at the results if two synchronous clocks at A are moved in a closed circuit with a constant velocity until it returns at its journey at A, so it completes a closed loop circuit. The journey lasting t seconds, then by the clock, which has remained at rest and traveled at A, will be 1/2 t times nu squared over c squared seconds slow. Hence, when we conclude that the balanced clock at the equator will be slower than the one that completed the circuit. So And what he's saying here with the balance clock, he's not talking about a pendulum. He's referring to a light clock. They didn't have atomic clocks at the time, but luckily we have atomic clocks now. So that's what he's talking about. The clock rate will be slower. So this is so now we have another instance where these equations apply. If you're in a uniformly rotating frame, then these equations should also apply. Now, Einstein does go on to say in his I think it's 1916, in his 1916 paper, he says that a uniformly rotating frame, applies to the general theory, but he never retracts this statement or goes back on it. And also Thomas precession is explained through special relativity, where it's basically infinitesimal link contractions that you can arbitrarily define using a Lorentz rotation, which is basically a way that you would bring the two frames back into alignment, because you're describing a rotation, so they're not going to be directly orthogonal to one another, which just means they're not going to be perfectly parallel and perpendicular to one another, that they're going to be like off tilted at an angle a little. So you're going to have to tilt it, and that correction angle, that tilt angle, would be the rapidity angle, they call it. And anyway, you could it's basically applying link contraction and time dilation to the orbit of an electron, and they call that Thomas precession. They call that rotation the Lorentz rotation, and you could do two of those to establish that rapidity angle, which will allow you to apply a Lorentz boost, which gives you your link contraction and time dilation. And they say that explains an orbital precession anomaly in an electron. So it's canonized, that special relativity can definitely handle rotation, and it should apply. And this will be important later when we look at the Sagnac effect. Any questions so far? I just said a lot.
Yeah, doesn't the reference frame change if it's rotating? Doesn't it have to be in a linear motion? Doesn't
the reference frame change? Yes, that's where they use the difference in the offset between perfectly 90 degrees and whatever the offset would be to bring it into alignment so that they're both orthogonal. So I think I have some diagrams of that. Give me 1 second.
I'd like to see how they did that.
Oh, it's just a math coordinate system. You check it out. So.
Oh, just math. Oh, gotcha. Okay.
Yeah. It's nothing too fancy. Check it out. Give me 1 second. Get you the visuals. Here we go. All right. So when you do a Lorentz transformation, you need both of these. If you hold up your finger with your index finger and then make an L with your thumb, right? You need that parallel and perpendicular relationship for your time axis and your distance axis. So your time axis would be your index finger, your distance axis would be your thumb, and to do a Lorentz transformation to consider link contraction and time dilation, the system that you're transforming to also needs to be in that similar alignment. Does that make sense?
Trying to understand it, but
okay.
I don't know how you can make a circular. Yeah.
So
I think I understand what you're saying, but
yeah. Okay. One sec. I got you. Where's my thing to draw? Oh, there it is. Oops. All right. So just imagine these are perfectly parallel and perpendicular. So this will be our time. This will be our distance. So the stationary frame would have to look like this for t and x, and then the moving frame would look like this. They have to be, Like if you were to add them together or whatever, I don't know. They just have to be at that alignment like that, right? But if you're in a rotating frame, oops.
So what? They just angle them, like they just vision an angling of it.
Yeah, because this is all just like coordinate systems on a graph, essentially. So the way that they would need to represent it, right? So suppose you're in a rotating frame like this, right? You see how the L, like the time and the distance axis, aren't exactly parallel and perpendicular anymore. They're not both 90 degrees to one another. They start to be offset.
Yeah.
So to fix that,
Look, I'm getting it, but I'm not buying it. Let's put it that way. But I get what. Yeah, the tilt.
No,
I knew it. Yeah.
Yeah, you're good. So if you were to line these up, right, there would be a theta angle right here, and you could bring these two back into alignment. Oops. So you could bring those two back into alignment, when you have that angle, and then you could do a Lorentz transformation and figure out how much link contraction and time dilation there would be in a rotating frame. Because you can take any section of this in rotation, and just arbitrarily define a time, and it's going to be, slightly different than in a slightly different position than the starting point, albeit it'll be slightly deviated because, circular orbit or whatever, but you can fix that and then still apply these equations, and that's all they did. So does that make more sense now?
I hear you, bro. I hear you. It's like, yeah.
Yeah, it's just, it's really important because modern relativists will deny, the Sagnac effect applies in a rotating frame. They'll say special relativity doesn't apply and all these things. But it's important to understand that it's canonized, that it does, and this is how they do it.
Yeah, I'm not convinced. I'll tell you that. But okay.
Yeah,
that's how they do it. That's how they do it.
Yeah, dude. I mean, it's it's not how I would approach things, right? But yeah. So that's just important to understand where the equations apply, because if you understand where they apply, then you can understand where they've been falsified, right? So that's the importance of that. And then we get into, I think that's basically it. So it gets into the velocity composition law for relativity, and basically you make it so that nothing can exceed the speed of light. So everything that's c plus or minus v will always work out to be c, or anything that's c plus v, will work out to be c. It'll still be c. So those are the rules and regulations of the theory. And with that said, so now we're going to get into a thought experiment that was proposed by Einstein that's called the bomb and train experiment, or thought experiment. So we'll look at that now. All right. So Einstein proposed a thought experiment where he said, suppose you have an inertial observer C, and we have a moving observer D in a train moving at a constant velocity. And at the same point that these two lads intersect, there's going to be a simultaneous event. A lightning strike will occur. I'm sorry, simultaneous lightning strikes will occur, and they'll both hit trees A and B, which are equidistant from that middle point, from that middle intersection point of the two lads at C and D. Excuse me 1 second. He says that for the observer in the train, the event will not be simultaneous, will not be perceived as simultaneous, because he's traveling towards the tree, and because of the constancy of the speed of light, it'll get to him first there, and because his frame has to be valid, right? That sequence of events that occurred in his frame, his perception of these events, also has to be valid as well. Otherwise, the laws of mechanics can't hold true in them, as stated by Einstein earlier. So, with that said, he does not, in his reality, there was no simultaneous event that occurred. Now, the stationary observer, of course, has no velocity, and when the simultaneous event occurs, he's in the same position. He's not moving closer towards either one of these lightning strikes, A or B. So the information gets to him at the same time, and he perceives the event as simultaneous. So it's simultaneous in his frame. And what you can do is you can apply Einstein's equations for length contraction and time dilation, which are really Lorentz's equations, which are really Voigt's equations, but that's a whole another history of fun. But anyway, you can apply these equations, and you could show that due to length contraction and time dilation, you can actually put the bomb back at the midpoint so that it's equidistant from A to B, and that it receives the simultaneous event at the same time. I'm sorry if I said bomb. I meant observer. I was thinking ahead. And then you could Lorentz transform and show that because the stationary frame has to show reciprocity, right? So you would apply the velocity from the train frame observer to the stationary observer, and also the sequence of events that would follow that would make him perceive the events as not simultaneous. You can show that. And this is a really interesting thought experiment. You know, it's very cool, but it's taking the apparent effect of relative simultaneity, right? Where and then making it a real effect. And what you can do is you can come up with scenarios to up the stakes a little bit and find a way to, take it to its logical conclusion, really. So a thought experiment that we came up with, well, other people have come up with it as well, but I'm not gonna take credit for it. But one that we came up with was a very simple one that, suppose you have a bomb on the train and it'll detonate if simultaneous lightning strikes occur. They will send a signal out that will reach the bomb, and it doesn't matter if the bomb is at the midpoint when it occurs. It's just dependent on the simultaneous event being true or not. And in the moving frame, you would argue that a simultaneous event relative to a stationary observer didn't happen simultaneously, and therefore the sequence of events is valid because relativity's equations are valid in that frame. So this would lead to a different sequence of events, so therefore the bomb would not go off. And you would have to you'd have to take that position that that if there was a stationary observer and there was a simultaneous event that occurred that was going to result that a signal gets emitted that would detonate a bomb on a moving train with another observer at that center intersection point, right, that would perceive the simultaneous event as different, you would have to say that person would be safe on that train. Now, would anyone feel comfortable getting in the train and testing whether or not relativity is true? I hear a lot of mixed comments on this, and I've only experienced one relativist who said that they would get on the train. Only one true relativist amongst all the others. So, any questions?
Can I play advocate devil here?
Yes, absolutely.
Okay, on your first slide, the first one with the bus, right?
Yes.
The train, sorry. Doesn't the thing state the theory state that light, the speed of light, is irrespective of the observer? So in this case, wouldn't they see the light at the same time, irrespective of the movement?
No, because he's moving towards it first, so he's going to receive that first. Like because the light's at a fixed speed over here, and he's not going to be in the same position technically. He's not going to perceive it as being simultaneous. So it's like, you could think about it like like Doppler shift. So like if you imagine two speakers at the opposite ends of football fields, and you were in the center of the football field at the 50-yard line, and you had a buddy that was running towards, or running by at that intersection point at that 50-yard line, and you could use a triggering mechanism to know that you're triggering the speakers at the same time. Your buddy would perceive that the speaker that he's running to happened first, but in reality, right, there was a mechanism that triggered, and they happened simultaneously.
Okay.
Yeah. All right. So there's been some points of contention about that whole situation with the relativist, and people saying that because we can Lorentz transform, we can make both frames agree on the physical outcome, because we all know instinctually, right, that bomb is going off if there's a simultaneous event. And before we move on real quick, an easier way to think about this would be with the balance beam. Battle of the beams. Relativity. There we go. So, you could get into like the philosophical argument of like, how would you know that the simultaneous events, do agree? You'd have to go have some way to go back and check or whatever. Well, remember, Einstein's equations apply in a closed loop. So, suppose you have a giant circuit, and a similar situation where you have balls A and B on a platform that'll be dropped out from underneath them. So they'll fall at the same time, and they'll hit a balance beam at sections A and B. And if they hit the balance beam at the same time, they both bounce up, and they don't have any deflection or deviations in their bounce. And if they do have a deviation, if there is a timing offset, they'll fall unevenly, and that will cause them to be deflected. When they hit the balance beam, it'll cause it to be offset, similar to like a teeter-totter, very simple and straightforward. So, suppose you have a track or something, right? And you could have a moving observer do a circuit, and based on his velocity, right, at that intersection point with the stationary observer, he's going to perceive that ball B is falling first. So in his frame, if the sequence of events is valid, then reality dictates that there's a different physical outcome here, that the balls get deflected. And what actually happens, right, is that they would just hit the beam and bounce back up, and it would agree with the stationary observer, which would distinguish between the two frames. And making coming to the conclusion that you can make the moving frame agree, and therefore it's valid, doesn't satisfy relativity theory, because remember, you have to have physically different outcomes and reciprocity between the two frames, meaning they have to be interchangeable on their physical outcomes so that they can come to this conclusion that the event was or wasn't simultaneous in their reference frame. And the only way they can do that is if the events that occurred, which are spatially separated from one another, the two lightning strikes or the two balls falling, two spatially separated events occurring at the same time, but perceived differently in different frames, have to follow the physical outcome of the perceived event in relativity theory. Now, this is a massive deviation from classical mechanics and the classical understanding, because time and space are absolute, and no one's ever experienced a physically different outcome due to a velocity. Any questions
Exactly.
or comments?
Yeah, exactly that. What you just said, your last sentence. Yeah.
I do like this example of Alan, because this has a rigid body. So if the moving observer were to see one end hit, it'll have a simultaneous effect on the other end. I will try to invoke a devil's advocate, though. I've heard a BS answer to this, that even though the moving observer would notice one end hit uh, causing the other end to lift up, the information has to still travel from one end to the other, and therefore it reconciles. I don't know what that means. I think it's a BS answer. I'm sure you've heard that before. What was that person trying to convey, and is that a good reputation or not?
No. So what they're doing is they're extending the time it would take for the information to go, so that they can preserve the physical outcome that agrees with the stationary frame, which so they're tacitly agreeing to absolute time and space by artificially inducing like a delay in the information and all that. Because that's not the relevant part of it. You can delay it as long as you want. That's why I said you could have the dude complete a circuit. You could have him never come back, or it doesn't, or you could have him like have a mirror that's looking back, and like, you know, eventually the information will catch up to him. But the important part is that is that it demands physically different outcomes, and if they both agree due to, you know, an imposed information delay due to a, you know, perfect rigid body of the board that's just preserving absolute time and space.
Correct. Yeah, it's the rigid body that they're not paying attention to. Delay it all you want. Have that vibration go at a Planck length per segment. It still has to travel up that rigid body where one end will respond with the other. So thank you for that.
Yep. Were you about to ask something, Essie?
Minimum time, a speed.
What's
like,
that?
Would there be like a speed, a minimum or a maximum speed needed?
No, so that's the cool thing, right? Relativity theory, right, is everything is arbitrarily defined, or time and space are arbitrarily defined as a function of velocity squared over c squared. So any velocity, right, these have to hold true. But what they would say is that, you know, if you're just like traveling in your car 50 miles an hour, you know, that's such a small velocity because the ratio of your velocity squared over c squared is going to be insanely small. So they're going to be like, you would never notice. They would be like imperceptible, right? So they would be talking like, you know, speeds that are close to the speed of light where the ratio would be, you know, more meaningful or whatever. And this is all hypothetical anyway, right?
Exactly. They would have to invoke speeds near the speed of light. Exactly. They can't use a train for this.
No, they could only do it in fantasy stuff. But actually, when GPS came out, like those measurements are so precise, and the timing is so, because you know they use atomic clocks that break a second down to 9,192 millionths of a second. So when you have that kind of precision, relativity of simultaneity timing corrections would have been a factor that they would have needed to account for. And guess what, dude?
Exactly that. Yeah, pure fantasy. This is pure fantasy. Yeah.
Yep. So if there's no more questions about relativity of simultaneity, we can move on. Oh, sorry. There was supposed to be some relativists here to, I don't know, you know, defend their position, but I guess they're all sleeping or busy or something. But,
Whitson, I thought we had a pseudo relativist.
Yeah. Whitson and Shane, do you guys want to chime in on any of this?
It appears their position has contracted.
Oh no, they dilated out.
Good one.
Crazy. All right, so that would be their position. So now that we've learned about relativity of simultaneity, we can move on to the twin paradox. So if the frames have to be equally valid and they have to show reciprocity, meaning because of the Lorentz transformation applying to a stationary frame, you should have the effects measured in the stationary frame as well. So if you've ever heard of Heffel and Keating, or, you know, experiments that prove time dilation through moving clocks, what you'll find is that all of these experiments are a one-way verification of relativity theory. There's never been reciprocal time dilation, which is absolutely mandatory for the theory. And we'll go over that in just a second. But what I mean by that is that how Einstein was saying earlier, that the moving clock that completes the circuit will be slowed by 1/2 times the velocity squared over c squared seconds, that also has to be reciprocal with the stationary clock. So that you would have to somehow show that that stationary clock received the time dilation and link contraction effects and the moving clock didn't, because otherwise you would be able to distinguish a preferred frame out of that. So it logically follows, you know, if you're going to follow that reciprocity and maintaining that all inertial frames are equally valid, including, you know, and going as far as defining an inertial frame as a frame that's actually in motion, then you have to be able to show that the stationary clock also receives these effects. And there's not a single experiment on this earth that's ever been conducted where the stationary clock went out of sync by the velocity squared over c squared when a clock completes a circuit. And that's noted in GPS. That's noted in all the experimentation that was done with atomic clocks prior to the GPS system, when they were figuring out how these clocks work, how to synchronize an absolute timeline, and how all that would work. They never once experienced a stationary clock having reciprocal time dilation effects. It's never happened. And that is absolutely required for any proof of relativity theory regarding time dilation. The reciprocal has to be shown. And further, when you get into time dilation specifically, you would have to also show link contraction is valid in the frame. And the reason for that is we went over earlier about Lorentz symmetry and the transformation equation, which actually, let me show you guys a picture of that real quick. Yeah, here we go. So this is the gamma factor. This is your link contraction and time dilation right here. So 1 over the square of 1 minus velocity squared over c squared. That's going to be the amount that the time axis and the distance axis are going to change as a function of velocity. So earlier I mentioned a graph. So earlier I talked about how all this is just kind of like plotted on a graph for funsies. So if you were to think about this link contraction and time dilation situation, you know, we could look at this graph here where we have the time for a stationary observer that's arbitrarily defined as the stationary frame for this analysis. And we have his distance axis, and there's going to be no change in them. And then we have x prime and t prime, which is going to be the moving observer. That's going to be defined as proper time. And in that frame, they're going to be experiencing link contraction and time dilation as a function of their velocity squared over c squared. And as you can see here, there's a little hyperbolic deviation between them. And this is what link contraction and time dilation look like when you plot it out, you know, relative to a stationary observer. This is what's being discussed. So, let's see. Sorry. So for time dilation, you have to show that both of those frames are interchangeable and the effects would be the same. So there was something I was going to bring up, but I suddenly forgot. Did anyone have any questions about? Oh, right. It was muons in Lorentz symmetry, right? So link contraction and time dilation, a successful Lorentz transformation that satisfies Lorentz symmetry changes both time and space. Those two axes have to change to establish space-time symmetry, right? It's titled space-time symmetry, not space and time or space-time. It's space-time because they're together and they have to be changed together under transformation for it to be symmetrical. That's extremely important because when you get into analysis of atomic clocks, they'll invoke one-way time dilation and they'll not, with no link contraction. So that's an invalid analysis or an invalid use of relativity. It violates Lorentz symmetry. And they'll do the same for the analysis for muons. They'll say that in the muon's frame in the atmosphere, it's traveling close to the speed of light, so it's experiencing time dilation, and the Earth is experiencing, the Earth in the atmosphere is experiencing contraction, and it's, you know, so it's moving towards the muon in its frame, and the muon appears to be stationary. And then from the lab frame, you know, you would say that the muon is moving and experiencing link contraction and time dilation. But when they get into measurements of muons in the lab, they only do the time dilation analysis. They don't apply the link contraction analysis, because it's obvious that you're not moving towards the muon at the speed of light. It would be preposterous to claim that. And so that analysis of applying relativity to a muon for an asymmetrical use of Lorentz symmetry it's invalid to use that as a proof of the theory. Any questions so far?
Well, I'd like to make a comment on the time dilation atomic clocks.
Yes.
I just want to make sure everybody knows that they literally just carried them on by hand, right? In propeller planes. They just put them on inside the cockpit, not the cockpit, inside where the passengers sit. And they literally took off and like, just like that. Like, there's nothing was controlled. That, like, I'm sure they couldn't control all the variables, right?
It's even worse than that, bro.
I know, bro, but I'm just giving them a little rundown, and you can like fill in the gaps, right? And it was off by 1/1000th of a second. This was how much the clocks were off. 1/1000th of a second.
Yeah. So, like, as he was saying, they just transported them to the planes, loaded them up, and then they didn't complete like a circumnavigation all in one flight. You know, they had to deboard, unload the clocks, transport them to the new plane, load them up, take off again, etc., and keep repeating the process. And then they actually ended up driving like the last 200 or 300 miles, I forget, but they ended up just driving the clocks home. And then throughout
it's comical, bro. Once you look into it, yeah.
And then throughout the experiment, the clocks all went out of sync with one another, like to different orders of magnitude, that it required them to actually just reset the clocks. So instead of them being, you know, out of sync with respect to the stationary clock, they all varied with respect to one another, and and they had such variances that happened, like I think it was like 12 or 14 times between them all, where they actually just had to reset them. So anything derived from that, and then so from the 1971, they were like, you know, the measurements were not in agreement with relativity theory. And then in 1972, after they made quote unquote post-analysis corrections, which they never revealed what they actually corrected for, they just present the refined data. They don't say, you know, what they corrected or how they made the data agree with their relativistic prediction, but they just present you with the refined data, and they're like, hey, check it out, boys, matches relativity. So that's pretty cool, right? And even in the 1971 paper, which was a debriefing that had to be FOIA requested, because the whole project was funded by the Navy. So it was actually by the Air Force, I think it was. So anyway, it was FOIA'd. So from the debriefing, even Heffel was like, yeah, this isn't very convincing of anything. And the fact that these original measurements disagree with the predicted values by such a magnitude, it's like no one's going to be convinced by this. And then the following year, all of a sudden, he's like, hey, boys, look where we found relativity, right where we were looking for it.
Imagine that.
Pretty wild. And then so to continue off of that, though, like I've been saying, though, there's this one-way verification of time dilation that they're trying to attribute to the desynchronization of these clocks. But actually, there's something called the Sagnac effect, which is, you know, relative motion is measured through the speed of light. So there's going to be a variance based on velocity. So if you're using an oscillation rate and you're an observer that's traveling at at some velocity, the oscillation rate of light is going to be retarded by a function of your velocity. And that is what they're accounting for. And that's a first order effect. That's not an effect of link contraction and time dilation, because remember, link contraction and time dilation are functions of the square of the velocity over c squared, which is a really, really, really tiny, tiny effect. And the Sagnac effect is directly proportional. So it's not a second order effect. It's a different order of magnitude there. So relativity doesn't have explanatory power over it, which we'll kind of get to towards the end here. So let's see. We went over the twin paradox a little bit there. So to close out on the twin paradox, no one's ever measured reciprocal time dilation, so there's never been an absolute confirmation of relativity's correctness. They use asymmetrical Lorentz transformations to give a relativity analysis, perspective on things, but obviously that violates the mathematical framework, and it's thus invalid and has no power over whatever phenomenon it's trying to explain. And when you get into the twin paradox, there's a really interesting history with it, where when issues were being raised about the twin paradox and they couldn't be answered, there was like 50 years of censorship from, let's see, let me get this guy's name real quick. I forgot his name, sadly. Twin paradox. Oh, Herbert Dingle, right. This guy, Herbert Dingle, starts questioning relativity theory, and he used to be a professor in relativity. He used to write all the textbooks for he wrote textbooks for relativity. He chimed in on other people's textbooks that wrote for relativity, that were, used for undergrad students and all that at university for everyone to learn about how cool relativity theory is. He wrote for the Encyclopedia Britannica for years. He was the specialist on relativity theory and breaking it down for the layman. And when he came across this time dilation paradox, what I just laid out, how the reciprocity between the frames demands time dilation and be reciprocated in the stationary frame, and even as noted by Einstein, where he says in a paper in 1922 that the effect has to be reciprocated in the stationary effect. So, it's fully canonized that's a valid interpretation. Dingle starts proposing, the twin paradox, where how does one clock get older than the other? How could reunited twins be both younger and older than one another? It doesn't make any physical sense because of this glaring contradiction in nature. This theory can't be true. And he was hella censored over all of that. Anyway, when you get into the people's answers where they tried to give solutions to this, there's 50 documented solutions to it, and none of them make any sense. Almost none of them refer to Einstein's writings, and they all contradict relativity theory. And most of them, end up establishing absolute space, or they'll say nonsensical things like the time dilation occurred before the velocity occurred, like just crazy shit. So that's there's no real answer for time dilation, and it's for the twin paradox, and it's never been, that reciprocal nature has never been measured in atomic clock experiments. All right, before we move on to the analyzing interferometry, does anyone have any questions about twin paradox, relative simultaneity, or anything else?
We can't close this without saying that one brother ages more or less than the other. We got to say that, right? Like that's the main thing.
Yeah.
And the implications thereof, right?
Dude, they always talk about like in the news, they'll be like, you'll see articles every now and then, like so-and-so astronaut that has a twin is now older or younger than his other astronaut brother who stayed behind on Earth because he was in orbit for a year. And it's like, bro, you guys are forgetting that has to be reciprocated somehow as well. So somehow the preferred frame is the Earth. And you can establish that guy was truly stationary.
Right, but not only that, bro. Not only that, because this is the thing, right? I'll be quick. One brother's on Earth, the other one gets flung out quick in a spaceship at near the speed of light, right? That's one of the ways. The other one is gravity, but we'll leave that aside for now. So that brother that is traveling at the speed of light, right? Time slows down for him, right? Then when he comes back, he finds his brother that's much older, right? But the meaning of that, the implications of this nonsense is that as the brother was traveling away at the speed of light, that means that the Earth had to spin around faster, right? For time to go quicker. Think about that. Think about the nonsense the implication that says, right?
It's a really good point. Because you're just imposing the velocity on them, so it's like you have to put some mechanism to it. Otherwise, it's just
like
nonsense.
the Earth would have to spin faster, for the brother at home to get older. Think about it. It's complete nonsense.
Yep.
I got a question. It's a two-parter.
Absolutely.
I figure now is probably a better time before interferometry. So, is there any precedent, meaning experiment or demonstration, to even suggest that physical space actually shrinks? And second, if there are, do these experiments show this phenomenon enacts an imaginary force on matter itself?
It's a great question. Let me get you the answer.
Sorry, what's an imaginary force?
When you just use your imagination and then use that to explain some physical effect. So we have here, Riggs.
I don't understand how I do that.
Yeah. Link contraction and time dilation.
Are you saying it's not true force? Or
link contraction and time dilation are supposed to be physically meaningful effects. So someone was raising a similar question to what you were asking, Riggs. And it was basically Einstein was chiming in to correct them and say, if you were stationary, you could measure the effects between, the link contraction and time dilation effects between the two relative observers. So hypothetically, you should be able to, and there isn't a single experiment that's ever been done to show link contraction and time dilation. It has to be pre-assumed as an explanation, right? Because it's really, it's actually a perfect question because we were about to get into interferometry, which is like the crux of where it came from, or where it's inserted to give explanatory power over as a second order effect. So when they didn't get the measurement that they needed, they were like, oh, you know what? We actually can't because link contraction and time dilation. So it's like you have to assume first that the velocity that you tried to measure was correct and that caused link contraction and time dilation. Did that help answer your question, sir?
Yeah, that helps to answer the question. Thank you.
Cool. So in 1887, they had done, actually starting a little bit before 1887, we could recap a little bit on the history of interferometry. So they had a measured value for the speed of light using a rotating cogwheel in a mirror that was 2 miles away. Based off of the pulse rate that was received, they determined that the speed of light had to be, it was within an order of magnitude of the current measured value that they say. So with that close approximation, they were like, okay, it must be, close to this value. So they started using that speed to derive velocity with interferometry. And one of the first experiments that was done was called the Fizeau experiment, and it was testing Fresnel drag, which is that the ether would be dragged by a material medium, and the velocity would be like the velocity of light would be plus or minus the velocity going with or against that material media dragging the ether. So using sunlight and a beam splitter and a tube of running water that the light could be sent through going with and against the water, they measured a 44% velocity ratio to the speed of light, which shows that they could measure, translational motion with light, right? And then so this was in 1859, I think, or 1850 or 1861, something like that. So this prediction was made in 1818 by Fresnel, and it states that the density of the elastic ether in matter is proportional to the refractive index squared. And that's how they came up with this, using the refractive index of water and the induction rate for light and how much it would be affected plus or minus based off of the velocity of the water. So they measured 88%, 44% going with, 44% going loss going against in relation to the speed of the water. So they measured the speed of the water going through the tube, and the hypothesis of this equation and experiment was that the density of the elastic ether would be proportional to the refractive index squared. So that was a crazy prediction here. So this is from a citation from a textbook from Modern Physics from Jackson something. But this is like noting the classical derivation for this, without it being a relativistic effect, because nowadays they'll try and attribute relativistic velocity addition to this, and they'll say, oh, because we can relativity it must be mutually exclusive to us. But we have here in 1818 the classic derivation and the reasoning behind it. So however they came up with this or whatever, very interesting. But they ended up measuring it and confirming it. So from that, they went on to test the velocity of Earth through this ether medium, and they didn't get a value that they expected. Any questions so far? All right, I'm going to get some water. Give me one sec. All right, so once they had their hypothesis and their math down for measuring velocity, they came up with an equation that they would use to figure out how much fringe shift displacement should be measured at the end of the interferometer. If the Earth is traveling at the velocities that are required to substantiate the Kepler's laws and Newtonian dynamics as applied to the sky. So what we have here is 2D times v squared over c squared, and 2D is just the length that light has to travel, so 11 meters. So 2 times 11 meters over a velocity of 30 kilometers a second squared over the speed of light squared, which in using the speed of light, they'll give you, that'll be tied to this right here. Frequency times wavelength. So this will give you the change in the wavelength that will be measured, that will cause that fringe shift gap, that will be proportional to this velocity. So this is how they're deriving that relationship in regards to the speed of light and how all that works with the ratio used and where they get it. All right, so using that information, they had their predicted value for how much fringe would be would occur if their Earth is moving at was it 30 kilometers a second. If you were using a yellow wavelength of light at a wavelength of 10 times or 2 times 10 to 2 times 10 to 7, there would be a fringe displacement of 0.05 fringes, which would be equivalent to 30 kilometers a second. So each fringe would be equivalent to about 6 kilometers a second. And they measured just over one fringe pattern, and they had an accuracy air margin threshold of 2 kilometers a second. So they were over their experimental air margin, and they were within, the experimentally valid results here. So they show us in this paper 6 days of measurement where they redefined all of physics over this. Obviously, there was other measurements, but they only, present these here. So what we're looking at here with this dotted line is the expected value to give them 6 kilometers a second. And then in the, and then what they, I'm sorry, 30 kilometers a second. And then what they measured is the solid line here, which is just over 1 kilometer a second. And you'll note here this sine wave. So we got north, south, east, west, and this is with respect to the orientation of the device. So you'll see here that there's equidistant numbers here. This is so that they could rotate the interferometer in the north-south orientation because the light makes a cross over top of it. So you'll have it orientated north-south. So when you're supposed to be parallel or perpendicular to the plane of motion around the sun, they were expecting to get minimum and maximum readings corresponding to the time of day. So what you would do is you would mark out the orientation with respect to the time of day, and you would use that variable to determine, okay, is there a speed difference when it's orientated in this direction at this time of day, and if so, does that difference change when it's not in that alignment anymore? So that's how they were manipulating the IV DVs there, to show that cause and effect relationship with the variance in the speed of light with respect to the assumed velocity. All right. So at the conclusion here, he says the actual displacement was certainly less than a 20th part, and it's probably less than a 40th part. But since this displacement is proportional to the square of the velocity, the relative velocity of the Earth and the ether is probably less than 1/6 of Earth's orbital velocity and less than 1/4. And what precedes only the orbital motion of Earth is considered. If it is combined with the motion of the solar system, considering which but little is known about with certainty, the result would have to be modified. But it is possible that the resultant velocity at the time of the observations would be small enough that the chances are much against it. And this experiment should therefore be repeated through different times of day. For different times a year. And it appears from what precedes reasonably certain that if there be any relative motion between the Earth and the luminiferous ether, it must be quite small enough to entirely refute Fresnel's explanation for aberration. Stokes has given the theory of aberration, which assumes the ether at the Earth's surface to be at rest with regards to the latter, and only requires the addition that the relative velocity, hot mic please, that the additional relative velocity have a potential, but Lorentz shows that these conditions are incompatible. Lorentz then supposes that the modification, which combines some ideas of Stokes and Fresnel's, assumes that the existence of the potential together with Fresnel's coefficient. If now would be legitimate to conclude from the present work that the ether at rest with regard to the Earth's surface, according to Lorentz, there could be no velocity potential, and his own theory would also fail. So what did we just read there, homies? So as we talked about earlier, there was experiments where they were trying to prove the velocity of Earth through space using a telescope filled with water, a telescope with a half-covered prism. Do we need to adjust the focal length of the telescope, et cetera, et cetera? And these were giving results that didn't give agreement with Earth's motion being the causal mechanism. In fact, there was, regarding Airy's failure in Arago with the half-covered prism, it could be argued that it was giving positive evidence that the Earth is stationary with respect to the motion of the sky, which is the reason that the starlight comes in at an angle already, and there's no velocity component of Earth. So what Michelson quickly points out here at the beginning of the paper is that to explain Airy's failure, Stokes and Fresnel had to say that suppose the stationary ether gets trapped in the telescope and it's bouncing around and it's carrying the light in the opposite direction of motion such that it's canceling out the effect that would be required to tilt the telescope to show that the Earth is the thing in motion, which is, preposterous and super ad hoc. And on the flip side of that, if you believe light is a quantized chunk or a particle or whatever, you would have to assume that when the light hits the telescope, it accelerates in the water, which is a violation of conservation of energy and momentum, which is, not a valid interpretation of physics. And Michelson points that out here, and he says, and hence, in order to reduce it to its true value, we must make the absurd hypothesis that the motion of the water in the telescope carries the light ray in the opposite direction. And he's talking about his position being an ether lad, being a wave lad for light. He has to make the absurd hypothesis that light is being carried in the opposite direction of motion to believe in the Copernican principle. So shout out to our boy for being very open about the interpretation and what has to be agreed upon to keep the Earth in motion. And then we have the commentary at the end here, which is saying that if you take this measurement as is, it's too big to say a null. It's too big to say zero. Like if you say Airy only had to correct his telescope by 0.08 arc seconds, 0.8 arc seconds, then, that's just experimental error. It was actually just no correction. Therefore, the relativistic interpretation is correct, where the water has no velocity potential. And it's like, okay, cool. And if you were to say link contraction and time dilation, these effects are much too big to fall under link contraction and time dilation, because remember, link contraction and time dilation are extremely small effects. And that's what Lorentz was originally proposing. That's what Lorentz symmetry is. It's the change in the time and the distance axis with respect to a stationary ether that's causing the compression of the molecular structure of bodies as they move through it as a function of their velocity squared over c squared, which is exactly what Einstein proposed in his theory, but he just removed the ether as the mechanism of the agent for the compression and said that time itself is arbitrary and changes as a function of the velocity squared over c squared as well as the distance. So that's the only distinction between those two theories. It's literally just the interpretation, but you can't even introduce those theories if you take these measurements as they are. Any questions so far?
Yeah, I mean, this is kind of a variation of why would they lie, but why such a concerted effort to hide ether as a mechanic?
Well, let's see here. Firstly, they were building astronomy on the constancy of C. They were building their, these ratios that they were measuring velocity with are based off of, a fixed value for C. So they were super into the idea that that the ether would keep that value at C, and they could use that to measure velocity, and they would be able to measure, Earth's absolute velocity through space. And that would confirm like the constancy of C, and it would confirm that you could that their interpretation of using C as a yardstick for astronomy was valid. And if you have a speed that changes, then you can't use it as a yardstick to make your assertions. So the big thing that sparked Airy's failure was stellar aberration, where when you take that angle and ratio it over the speed of light, you get 30 kilometers a second. So they were super stoked about that because you can interpret that as the causal mechanism being Earth going around the sun at 30 kilometers a second, right? That gives good agreement with Kepler's laws and applying Newtonian dynamics, where the dynamic cause of the velocity is mass attracting mass, and that's going to produce that 30 kilometer velocity. So that's like good agreement for them. So when they introduced water with the telescope, they were supposed to have a further correction angle on it. And they didn't get the correction angle that gave agreement with the theory. So it was all in an effort to keep the speed of light a constant because of that that belief system and what they were doing with physics and attributing dynamics to the heavens. They were going to lose all
It
that.
sounds like it goes back to that whole like philosophical preference thing.
Yeah, it certainly does. So yeah, without without calling this a null result, because if you start reading physics textbooks and different papers and whatnot, you'll see a common theme in all of them is that Nicholson-Morley was a null result, and that it measured that the speed of light is constant. But here we're looking at the measurements, and it's showing that the speed of light changes throughout the day, and it has a velocity difference of about 6 kilometers to 8 kilometers a second. So you can, and then knowing the 2 kilometer a second sensitivity, they were within, like, it's perfectly valid to interpret this as the Earth being stationary with respect to a dynamic ether wind.
Unless, of course, you have a philosophical preference.
Yeah, unless of course you want to keep the Earth in motion. Exactly. It's blind adherence to the Copernican principle. And you got to remember, all these papers, all these experiments, all this is like trickle down stuff that we're getting from the Royal Society, that all have a specific belief system, that all have a vested interest in controlling information and how they're presenting it to the public, so that what their overarching interpretation of reality is supported by all of this.
Yeah, when Gilly showed me the history of the Royal Society and all of the people that came out of the Royal Society, it's like every single piece in the puzzle starts there.
Well, dude, it goes back to our boy Herbert Dingle, right? When he was questioning relativity theory, back in the, what was it, like the 50s and 60s, he was trying to publish against the Royal Society in Nature, and John Maddox was like, "Hey, buddy, you can't question the Royal Society. What are you doing? Like, I'm not going to allow that in Nature." And then he just started gaslighting the guy, and he couldn't get any resolution from the Royal Society or from the press council, from like the actual like royal family or whoever's in charge of the press over there. He was like trying to get them to, intervene, because what that dude was doing was unethical. But they all came to the conclusion that what John had done was not unethical, and it was all good. And basically the sentiment was, you're not going to come here and question everything that we're building upon. And then, so it came to the point where Herbert had to write individual letters to his 300 fellows of the Royal Society, making a personal pleading. And he was like, "Look, boys, I've been trying to get a resolution to the twin paradox. Nobody has an answer. People write me in private to try and give an answer. And the reason they're writing me in private is because their answer is retarded. And if they were to say it out loud, they would get clowned. So there's no actual answer for this. And if there's no actual answer for this, this theory can't be physically true, because nature doesn't have contradictions, and we need to throw it out and like make, and figure out a different theory or figure out a different aspect of it, because, this is just invalid. So if anybody would like to help me out here and comment on this and urge the Royal Society to comment on this, that would be great. Out of the 300 people, only 12 people replied, and 10 of them were like, "Yo, bro, that sucks. Sorry about your luck. It's real unfortunate. Catch you on that flip-flop, dog." And, just no resolution or help. And there was 2 lads, I forget the other guy, but the one guy was like, "Yeah, that's hella fucked up. But relativity, seems to agree with experiment. So I don't know why it's wrong, but I choose to believe it." So shout out to that guy for at least, being like, "Hey man, I don't know why either, but I agree with it. It doesn't make sense." But one guy got his friend, a professor named John McCree, to comment on it and write against it, and allowed the public, and because he was willing to write in opposition to it, they allowed Herbert's initial publication to be published in Nature along with the refutation. But the refutation wasn't very good, because it ended up not agreeing with what Einstein said about how it has to be reciprocal in both frames. McCree argued against the reciprocity of that, so he wasn't in agreement with the theory, and there's not actually a good answer to it. But it's like, that's what it took to even get something published against, you know, something this devastating and this glaringly obvious. Like as SE was saying, you can't have the twins be both younger and older with respect to one another. That's retarded. Like a 10-year-old could understand that, you know, and if you could understand that level of how this theory is falsified, like at that basic level, like you know, they can't have that getting out, you know what I mean? Because it's very obvious that that's not true in nature. And if it's not true in nature, then time and space are absolute, which is completely antithetical to changing distances and times based off of a function of velocity.
So everyone was afraid of anybody in the Royal Society because I guess they probably made all their money from funding from that one group, or you know, things associated to that one group, like colleges that are funded by it.
Yeah. Yes, sir. Yes, sir. All right. Let me check the YouTube chat. How we doing on questions, comments? Yeah, dude, you guys all have mod. If people come in and act like shitheads, just slay them. That's the policy. So anyway, so yeah, so this experiment was explained through link contraction and time dilation. But we have the measurements here that directly contradict that theory. And we've shown that relativity of simultaneity doesn't have a physically valid interpretation. And almost everyone that interprets it now preserves absolute simultaneity by saying that both frames agree, which is a misinterpretation of the theory. All right. All right, well, I guess we'll just do Sagnac, DeFore, and Wang, and we'll wrap all these up together as a uniform thing, and then we'll get into GPS and close out. So let me pull up Wang.
So are you for relativity or against it?
Against.
You're against it, right?
Yes. Correct. All right. So we talked about how Einstein's equations apply in a rotating frame. Perfectly valid to do that. There's already examples of them with Thomas precession, etc. So in 1913, there was an experiment done with a rotating interferometer that showed that the variance in the speed of light was proportional to the rotational rate of the interferometer going with and against the rotation, which is a measurement of absolute space, because that's the only way that you could make the measurement. And then in addition to that, it was hypothesized by Sagnac that the explanation for this is that the ether encompasses the Earth like the atmosphere, how they say that it moves in lockstep with Earth's rotation. His hypothesis was that the ether was like that and it moved with Earth's rotation. But within that, there could be winds where any velocity would generate its own optical vortex, which would create, its own ether wind, so to speak. And that's what was being measured here. So he published in 1913 that he had experimentally falsified relativity theory based off of this measurement and based off of the optical vortex as the explanation for the mechanism for that the light was being dragged with the rotating interferometer, or that the ether was being dragged with the interferometer, and that gave that proportional that allowed that proportional measurement to be made. So again, remember that Einstein's equations, if applied properly in this frame, would predict that there is no observable fringe shift pattern because the speed of light has to be a constant. So despite the rotation of the device causing a path length change in the distance traveled, the speed of light traveling at the same speed in both directions with and against would complete the circuit at the same time and recombine and give no fringe pattern. They would be in phase still. And further, if they applied in the sense that link contraction and time dilation applied, it would predict a much, much smaller fringe that would be a function of the velocity squared over c squared, which is, insanely small in comparison to what's actually measured. So when we take a look real quick at the classical derivation for the Sagnac effect versus the relativist derivation. All right. So for the classic theory where you use absolute time and space to make the measurement against, you can account for the speed of light difference based off of the path length change going clockwise or counterclockwise with respect to the timing difference, which would give you the fringe shift pattern. So the speed of light is going to be different going with and against the rotation, and you can reduce Sagnac's equation down to delta z, which is just going to be delta, the change in the fringe pattern, the change in time. The timing difference is going to be equal to 4 times the area that the light has to travel, so just the path length, times the rotational rate over the speed of light, which is going to give you the ratio for the fringe displacement. That's going to be your delta z there. So following this equation for delta t going with and against clockwise and counterclockwise, so we got plus and minus. This is your clockwise and counterclockwise for the rotation rate. That's going to derive the timing difference, which correctly predicts the fringe shift pattern. Very cool, very straightforward. And then if we take relativity's principles, where the speed of light is constant for inertial observers, well, we have the rotating platform at a uniform speed. So if we apply the relativistic principles to derive the timing difference for 2 inertial observers, we're going to have the timing difference is going to be 0. It's not going to predict a path length change because we can't use an absolute frame for the timing difference to be relative to. So it's just going to complete the circuit at the same time. All right, so that is the proper relativistic interpretation of how to derive the Sagnac effect. There isn't one without invoking a preferred frame, and in fact, we'll look at the explanations given real quick. So we have here. See if I can find my Engelhart or not Engel. Yeah, right here. So we have Niklaus in 1993 where they were talking about there's 21 different citations here of people trying to give a relativistic derivation for the Sagnac effect. It's never been done because the theory actually predicts no fringe shift pattern in a rotating platform. And you can only explain it by invoking a preferred frame, a fictitious frame, which is explicitly, against the terms and conditions, which we went over earlier, where he was saying, I'm not going to assign velocity vectors for electromagnetic processes, right? But that's the only way that you could do this. So we got our list here of all these different derivations of people trying to explain it. And the one that they went with for a while was Paul Langevin in 1918, who said, using the general theory and a rotating frame, we can fully account for this. But what he did was invoke a fictitious frame. He used a cylindrical coordinate system to transform to invoke a fictitious frame at the center where he could watch the speed of light be different for an observer at the rim of the device in motion, which is explicitly what, Einstein said his theory was against. So we'll take a look here at a couple of explanations that try to explain the Sagnac effect, because this rotational effect was actually measured. There's actually a linear variant that was measured in 2004 by Ruyong Wang, which we'll get into. All right, I don't have the slide for that right now, but one second. So remember, Big Iron said any closed polygonal loop and his equations are good. So a rotating interferometer is perfectly valid. But here we have an even more straightforward scenario, especially this configuration down here at the bottom, this parallelogram, where only the linear portion is moving, and only the linear portion makes the correct measurement for the length that's used, not the total length of the apparatus, showing that the measurement is not made with respect to the total length between the apparatus, the linear portion and the detector. It's only relative to this portion of the apparatus here, to the part that's in motion. So it can't be relative to itself, because otherwise time and space would be absolute in that regard. So we're going to look at some explanations that people have tried to give that explain the Sagnac effect and explain this effect. But as we're going to see, that this is all done with fictitious frames, which explicitly violate the terms and conditions. So we'll start off with our Arbori Tartiglia in 2014, I think it was, where he tries to explain the Sagnac effect and and Wang's measurements. So what he does here is he gives the classic derivation, which we went over, very similar formalism. They're all describing the same thing about the path length change, going with respect to counterclockwise and clockwise. So he's like saying here that C plus or minus V was a perfectly valid interpretation, very easy, and all these things. And then he goes on to say that we can invoke a geometrically convenient position here using the surface of a cylinder to be aligned with the axis of rotation of the interferometer. And using that, we can set up for our deviation. So if you guys remember that graph that we looked at earlier, where we had the time axis here for the stationary lad, and we had the deviation for the moving lad with T prime over here. This is what we're looking at. This is setting up a fictitious frame at the center of the device where where that's not actually where the observer is in that scenario. But this is what they, have to do to try and allow for the first order timing difference to explain it, because otherwise their theory doesn't predict a fringe and it's useless. So here we've already stepped out. We've already violated relativity and thrown it to the wind. And then he goes on to conclude here that, oh, you know what? It's actually all good. And if I throw the gamma factor in at the end here, which is too small and cancels out, where was that at? One second. Yeah, right here. So he throws in the gamma factor, which is too small and irrelevant, but this would be your link contraction and time dilation. Yeah. But he has the full timing difference attributed clockwise and counterclockwise with respect to that frame that he invoked earlier. So anyway, he's just like throwing in that, and he's like, oh, look, it somehow works out just fine. And the Sagnac effect can be explained in terms of different speeds of light in a co-rotating and counter-rotating directions if the clock along the rim of the disk are Einstein synchronized in the terms of the time gap of different synchronization procedure are used. So he's totally just like, yeah, you could measure linear motion. It's totally fine. Like that. It's like the biggest code.
And this is after.
Go ahead.
Sorry. This is after he put in a fictitious frame.
Yeah. Yep. Yes, sir.
You said earlier, right?
Yep.
Yeah.
Yep. And then a term here that's completely neglectable. The gamma factor has no explanatory power, but they throw it in there and they're like, oh, because my gamma, we're good to go. And it's like, nah, bro. Gamma is a second order effect. This is a first order measurement that has a timing difference that can only be explained when it's with respect to absolute time and space. So GG, man. So anyway, what they tried to do here though is invoke in the parallelogram configuration, they invoke a midpoint observer for their fictitious frame in this analysis. And then we're going to see a pattern of that was recently done in 2022 by Berida and others, where they're like, all right, look, boys, we got the old Sagnac here, and we can't really explain it using the relativistic effect unless we do the old geometrically convenient transformation here. And they go on to say that, though it's difficult to, or though they can explain it mathematically, the physical understanding of the effect from the standpoint of the observer attending the rotation remains difficult. In other words, if the speed of light is constant in these frames, how are they possibly measuring a fringe pattern displacement? It's directly in the face of the theory. And they invoke this midpoint here to explain the Wang interferometer again. And it's like, okay, with respect to what though? It's always, the measurement has to be made with respect to absolute time and space. Otherwise, otherwise it wouldn't exist. Relativity would be true. It wouldn't be valid. So there's, in 2022, there's still no valid relativistic derivation for the Sagnac effect in a rotating frame or for Wang's measurement. And then there was a more modern one in 2024 here, where this lad is like, hey, I got you, bro. I'll explain it. Let me see. Is this the right one? History, simultaneity. Yeah. So what this gentleman does, very confusingly, he tries to explain this as an effect of relativity of simultaneity, saying that each time the beam hits the beam splitter as it's in rotation, that's creating like a different synchronous simultaneous event, and therefore it's like the beams are starting at different times, and that's creating the timing separation. Although that's like, he even says that's pretty crazy. But let's take a look at what he does here for the fictitious frame to even get to that point to start talking about a timing difference for relative simultaneity. So he says here that, because it's a rotating frame, he does the classic relativity doesn't apply. Therefore, we have to use the general theory. And when you're using the general theory, you're using curved space-time, which is denoted by this right here, which is G mu nu, which is the curved space-time metric. And what he does is he starts taking differentials from the coordinate system that this supplies, because this supplies a curved coordinate system, XYZ coordinates that are curved. But if you take differentials from them, you can get infinitesimally flat sections of it. So he's saying that special theory of relativity, which is flat space-time, doesn't have any explanatory power here. But what we can do is we can use this curve metric and we can make it flat, and then, use link contraction and time dilation. So what are we going to do? What are we going to do with this newly found infinitesimally flat coordinate system? That's definitely not any flatter than flat space-time. We're going to use a ds squared here. So we're setting up for an inertial frame for a cylindrical coordinate system. So when you see a ds squared, we're describing a cylindrical coordinate system, spherical coordinate system, that kind of stuff. So we're invoking another center point again for there to be the fictitious frame. And then we're going to get into all this some nice integrals here of the timing difference going clockwise and counterclockwise. And suddenly we're going to have the explanation that we're looking for why there's a timing difference in the beam phase. So, regarding the modified Sagnac experiment from Wang, the explanation is no more puzzling than the relativity of simultaneity itself. It cannot be considered an inconsistency proof unless we declare relativity of simultaneity inconsistent. Well, we certainly do declare that inconsistent, and the hypothesis that this is due to infinitesimally simultaneous events being created due to the rotation is insane, and again requires an absolute reference frame to even have all of the infinitesimal events be relative to. So again, no explanation, absolutely nothing. All that fancy math, all that fancy, we got to use the curve space-time and make it flat. Nothing, has no more value than the algebra used in the original transformations.
Bro, I heard some swift talking and some hustling, but this this new stuff there that let's pretend it's curved, but let's make it straight and use part of this one, and that is like magic tricks, bro.
Dude, that's the classic, bro. So it's like, no, we can't just simply set up a cylindrical coordinate system in flat space-time. No, that's retarded. What we need to do is use infinitesimally flat sections of a curved metric that's equivalent to flat and do the same thing with a cylindrical coordinate system. Like what? Why? So that we can continue differentiating between a rotating frame as being an acceleration and dividing acceleration in constant velocity to keep the two theories separate so that we can have different explanations for measurements to keep our philosophy alive. It's like, all right, well, that makes sense now.
Bro, I'm going to need an aspirin after this, honestly.
One of the apologetics I've heard. Opioid. One of the apologetics I've heard for your good question about why is there infringement pattern if C is invariant, and as well as the problems with absolute space, is that with the Sagnet effect you can account for that being it relative to itself. And would you agree that in order for there to be some type of relative comparison, that you can't have it be relative to yourself? You need to compare at least two things.
Sorry,
agree on that, or
sorry, say that again.
Yeah, with the explanation with the Sagnet with the circular motion is that they made the reference frame being they're comparing it to itself, to its own velocity, and from my understanding, you can't compare something to itself. You need to compare it to something else.
So they make the exception there because in their philosophy, rotation is absolute, which makes sense because if you're rotating something outward, anything radially outward from that center point of rotation, it's all relative to that center point. So it makes sense, that there's an absolute frame for rotation in that regard. But then they make the leap in logic that, well, rotation and linear motion are completely separate, and somehow the universe makes a distinction between the two such that if you're walking in a straight line, you're not going to have any way to distinguish that velocity. I'm sorry, if you're just like moving in a straight velocity or whatever, not walking, you'd be able to tell if you're walking. But let's say you're like in a conveyor or whatever, moving at a constant velocity. It's like, are you moving or is everything moving around you type thing, right? So, shoot, I just lost my train of thought.
Circular motion being relative to that center point.
Oh, yes. So they're saying in the linear aspect of it, you have nothing to compare it to, so it would have to be relative to something else. So you would have to be like, oh, is it relative to that tree that I'm passing by? But then you would take the frame of the tree, and show the equivalence to be like, the tree could be moving or I could be moving, right? So, right. But for linear motion, and especially in regards to the Earth moving through space, there's no tree or anything like that for them to compare to. So they had to use the ether frame, for the comparison. And because they didn't get the measurement that they needed, they were like, oh, well, you know what? There must not be an absolute frame for this type of comparison for linear motion. And it's only applies to circular motion because that has a fixed point of origin.
But the tree thing only works if you act like you don't know anything else and there's no one else and it's just you and the tree. Once you mix in another person going at the tree and you're going at the same tree, then you have then you know things, right?
Well, if you establish absolute time and space for you and the other observers to, compare, the motion of the tree or whatever to, right? But if you're a relativist, you only do two-party analysis, right? So you wouldn't be able to come to that conclusion because
if you're on a ball.
Go ahead.
Because what?
Well, because in relativity, time and space are functions of velocity, so it would just be each person would have their own individual timeline and distance.
But If we're free falling though, if you're on a ball and you're free falling and they're antipodal to each other, you know what the movements are. Like it's not the ground, you know what I'm saying? Not the ground coming at you. Right?
Yeah, that would be like a kinematic supposition to argue like outward expansion.
I'm just saying this whole thing where it could be the tree moving or you moving is like, that's like if you act like you're the only one and you can't communicate with anyone else and you don't know anything else. You know what I'm saying?
Yeah.
So, in conclusion, the last question I'll have, obviously, we know we can invoke, Galilean reality with classical mechanics to explain everything. We don't have to have any added interpretations or invoke any special transformations. What would their objection be aside from that'll break my model and my fantasy land won't work? What would their objection be if, hey, our interpretations could have less assumptions, we have an absolute reality? What would be an objection to a heliosentence besides the obvious? Do they have any valid critiques?
No. They can only deny the measurements. Like ironically, they have to become science and measurement deniers.
Irony, right?
It's pretty wild. So
when they invoke the Lorentz contraction or something, what measurement?
Yeah, so
I missed a lot of your presentation I was doing, so I'm sorry.
Yeah, no worries. So all interferometry measurements that show that the speed of light is not constant. So Michelson-Morley, anything that claims to measure rotation, all of those measurements there's only a variance with respect to the east and west axis, never in the north-south. So that eliminates Earth being the causal mechanism of the rotation, because in their current interpretation of how it works, the speed of light is constant, and it's the Earth that's like, essentially rotating out from underneath the light to create the fringe pattern displacement with respect to the east and west directions. So in that interpretation, if the Earth were actually truly in a different location from when the signal was sent and received at the mirror to make the fringe pattern, you would have north-south variance as well. And there's never once been north-south variance ever measured. And then when you get into GPS, they only make corrections that are east-west. The signal going north-south never has to require any rotational, quote-unquote, rotational corrections, which would absolutely be mandatory because you're on a rotating sphere. So even if you're north-south or east-west, right, you're going to be still experiencing a physical displacement, albeit it'll be slightly less than what it would be if you were moving north-south, right? But you're still going to be experiencing it. And at the timing interval that these measurements are made, especially with GPS, that's going to have to be accounted for. And and it isn't.
From the Coriolis effect?
No Coriolis effect accounted for at all, sir, in there.
I'm saying, is that why the timing would be off, should be going off north-south in the globe because of the Coriolis? Or?
No, it would be off because you're physically in a different spot.
And the light didn't rotate with the Earth?
Correct. Because their explanation for the east-west variance is that it's rotating, with and against the Earth. So the light traveling at a same speed, it now has to travel a different distance. So that's their explanation for it without invoking. Well, they actually have to invoke a preferred frame at the center of the ball, but we can kind of ignore that for a second and just look at the reason for the displacement that they're claiming. And it's that you're physically in a different spot, which would dictate a north-south variance as well, because you're physically in a different spot. You're on the rotating sphere. It can't be the same in north-south, but different in east-west if you're on a road, if the ball is the reason that the rotation, or is the reason that the timing difference is happening in the east-west sections.
So you shoot the light, and then by the time it gets to the end, if it's going south, let's say, the thing's in a different spot, and it should have taken longer to get there.
Yep. Yeah, because the whole apparatus itself is moving, not just the east-west arms. Would you like some diagrams? Can whip one
I
up.
don't know how interferometry works, so I don't know.
Got you. Perfect. I'll make a diagram and help you get it. Okay.
And this is supposed to be able to measure, what can this measure? This should measure rotation, orbit, all types of stuff, or?
Yep. So this, they specifically say this is for rotation. So let's see here.
What's the one that can measure the orbit? That's the one I'm really.
So the one that they say was
Or that they
trying
had to invoke the Lorentz.
Yeah, the one that they were trying to invoke that for is for a Michelson-Morley style interferometer. That's where the light creates a single right angle to itself. And then when they came up with a closed loop, which I'll show you here in a second, they say that the closed loop can measure rotational rates, but not any orbital rates. And they make the distinction and say that because the orbital path is so big, right, it's basically linear. So they say that the Michelson-Morley interferometer, when light is at a right angle to itself, it can't measure linear motion because of relativistic effects of link contraction and time dilation, and the speed of light being the same in all directions. But when they get into the closed loop, they say, oh, you know what? Actually, it can measure rotation and will allow for an east-west variance, and we'll say that that's Earth rotation. But they don't attribute any velocity to it. They only look at it in terms of the angular displacement, because if they were to attribute velocity to it, it would be way too fast because they need the ball to spin at 1,000 miles an hour at the equator based off of the circumference. So they look at it as 15 degrees per hour for the angular displacement. And how they got that was from plotting the variance in the speed of light, the minimum and maximums throughout the day against sidereal time. And when they do that, they got a sine wave, and so what their interpretation of that is that, okay, ball rotates to create, what we see in the sky. Therefore, we must be measuring ball rotate. But obviously our interpretation, my interpretation specifically, would be that ball stationary and that sky rotate. And then obviously, being a flat earther, it would be an ether vortex that's spinning with respect to the time of day, and then that would be the measurements or whatever that they're making. So let me get you a little diagram going here. Where's my...
So they only have they time this by how long it takes to get there and back.
Yep.
There you go. That's a good angle.
Yep. So and then north, south. All right. So what they have here is the light starts here.
Yeah.
And let me make it a different color so you can see it. So the light starts here, travels to this mirror. It actually hits a beam splitter. So there'll be one beam going this way. And there'll be another beam going this way. We'll make this green. So these two beams will be split in different directions. Well, it's the same beam, but it gets split in two different directions. And they will complete their circuit around this in the east and west directions, and north south as well. And when they hit this beam splitter, or it's the opposite of a beam splitter, just recombines it, it splits it back, and it gets projected onto a photographic plate. And from this, because the beam started in phase, when it gets recombined, they can tell if it's out of phase by the gaps in between the fringe pattern. They call that the fringe pattern. So if it measures like a solid pattern, that means that the beam's recombined in phase and there's no fringe. But if they measure little gaps in the fringes like this, let me pull up some gaps here.
One of them took longer to go around.
Yep, exactly, precisely. That means that one of them took longer to go around. And what they can do actually is they can measure the distance between the fringes, and they find that that's proportional to the square of the velocity in question. So when you get
Why would one take longer to go around though? Sorry.
No, you're good. So one would take longer to go around if, for example, if there was an ether wind and it was creating a preferred direction where the light would be faster traveling in one direction and slower in the opposite. Or in their case, where they're interpreting it through ball rotate with a constant velocity of light, it would be that there was like a physical change in the path length to change the timing such that that causes the arrival of it at a different rate.
But both the beams got to do the same thing basically. If there
So-
was some effect on it, wouldn't it like equal out?
So that's a great question. That's why the measurement has to be made with respect to absolute time and space, so that you could get that timing difference between the clockwise and counterclockwise rotation. And relativity explicitly says that it doesn't need a fictitious frame to explain that. And that's a huge aspect of it as to why there's a timing difference.
Can you even get that? Can you even get that to get back? Has anyone ever got it to reconnect and be in phase? Is that even possible?
Yeah, so when you get to the linear, when you get to the Michelson-Morley style ones, so the ones that are at a right angle, let me show you that. So if you have, let me move this down. So if you have an interferometer that's at a right angle to itself, oops. Just want to draw a line. All right, so we have light at a right angle to itself. It gets split and recombined. All right, what was your question again?
Has anyone ever got it to?
Oh,
go
right.
back
Has anyone?
and
Yes. Has
further?
anyone ever? Yep. Thank you. So the original measurements from Michelson-Morley with this style setup, where light just does a single right angle to itself, they've measured a velocity of 6 kilometers a second. So they measured it being, out of phase. And then that experimentation was continued on by a guy named Dayton Miller, who reproduced the measurements, showed that there was a periodicity to them, meaning that they fluctuated with respect to the time of day and also where the position of the sun is throughout the year. But but in tandem with that, they had to deny these measurements because the relativistic interpretation was that Michelson-Morley actually measured a null result. So they measured no phase difference, even though there was. They interpreted it as a null. And then subsequent experiments have been done where they took what Dayton Miller found about how you can use different shielding for the interferometer and different mediums for the light to propagate in to cause different effects, where it reduces that fringe pattern down and it gives the appearance that it's recombining at the same time, and that there's that there's no variance. So they take those interpretations as correct because they've already asserted that the speed of light is constant, so they should be expecting to measure no fringe. So when they do the things that force effects that cause there to be less and less of an effect of the fringe, they take that as okay, we're measuring it correctly, but they never measure a full recombination. There's always variance, but they just attribute that to experimental error, and then they'll say within experimental error it's zero. Makes sense?
I have a question whenever possible.
Absolutely, Lily Poppins.
Now is good?
Yeah.
So basically, with the theory of relativity, are they getting us to believe that if I'm on a train and I'm watching, it appears that the trees are going by and I'm standing still in the train. And so basically, they're getting me to believe that it's the trees that are moving and I'm the one that's still. So when in reality, really, the trees are the ones that are still and it's the train that's moving. So, I mean, like if I had to explain to a 10-year-old, would that be kind of an accurate analogy to say that this is what they're trying to get us to believe with the theory of relativity is that both scenarios are the same. So basically, they're saying that whether the trees are moving and you're still, or the trees are still and you're moving, it's all the same thing. Whereas in reality, it's not the same thing.
That's precisely what they're saying. And they're saying that you actually can't even distinguish between a stationary frame because that doesn't exist, and all motion is relative, and you can only arbitrarily define stationary with respect to some other thing that's in motion.
Yeah, but that don't that's what I was saying earlier. That only works if it's just you. If you have another guy going at the tree in an opposite direction, you would know the tree is not moving. If
Yeah,
I go
but
60 miles at the tree and you're on the other side of the tree going 60 miles at the tree,
well, no,
we would know.
You wouldn't analyze it like that in relativity, though, right? So you wouldn't have that combination of things that would be the velocity relative to you and the tree, and then the velocity of the other guy relative to the tree. You would never combine your two timelines like that.
That's what I'm saying. They make it so it's like you're a caveman, so you can't know anything. You know what I'm saying? In the meanwhile, in the real world, we can know the tree doesn't move because we can both go at the tree at the same speed, and you know what I'm saying?
Mm-hmm.
Find out the tree didn't move and we were moving.
Yep. But so back to the interferometry aspect of it and what they're measuring with the rotational aspect. So when this now completes a full circuit instead of just a single right angle, they're saying that this is somehow different than just the single right angle. And this allows them to measure an east-west difference where they get the where they say, okay, we measured Earth rotation in sidereal time. So we look at here of the data set that they have. Oops, zoomed in a little too far. Did it again. Very nice. All right, so we look here at the data set, and this is the minimum and maximums throughout the day. And when you plot that against sidereal time, that's where they're like, okay, so this must be due to ball rotate because, in their cosmology, the only thing that's rotating that this would be measuring would be the ball. So this is where they get those measurements from. So in this interferometer, where it's a closed loop circuit, they're like, okay, we can have an east-west variance. It's allowed. East-west variance. But if it's at a single right angle, that's not allowed. No variance. Right? And to explain
The right angle one.
Yeah. Sorry, go ahead.
Quick, the right angle one was the one is that the one where they keep doing it lower and lower in elevation because the higher you get, the more of a variance you get? Is that the same one or is that a different one?
No, that's exactly it. That's exactly it. Let's see here.
They get a smaller fringe, smaller fringe pattern the lower you get, but then the higher you get. And then does it also change with the seasons the lower you get, or is it just more stable all around the lower?
So yeah, it changes all throughout the year. So there's an annular periodicity to the minimum and maximum speeds that corresponds to the position of the sun, where on the equinoxes, the speed of light reaches its fastest and slowest peaks. And then throughout the day, there's minimum and maximum peaks that correspond to sidereal time. So it shows
is that even underground though?
Yeah. Yeah, in modern interferometry, they take the closed loop ones because they're so sensitive. Because here's an issue with the setup, right? With this right angle configuration, because it only has so many points of contact with any sort of rotational aspect, there's a sensitivity issue here. So what they can do with a closed loop, because there's technically an infinitesimal amount of points that would be in alignment with any sort of rotation, it's more accurate or whatever. So when they use these now, and because it's canonized that they can have the variance there, they take these down into basements and stuff, in laboratories and whatnot, and do measurements with these, and they'll say, oh, this one's measuring the Chandler wobble, this one's measuring earth rotation, this one, all these different things. But they're all measuring, the same thing. It's just that periodicity fluctuation, because that's what produces the measurement. And I swoop that up as ether wind, whereas they have to attribute it to Earth ball rotate with no velocity component.
So how many wobbles are there, and what's the intervals between them? I know the main wobble everyone knows about is like 72,000 years or something.
Yeah, I don't know them off the top of my head,
Precession
but
of the equinox.
there's the nutation, the Chandler wobble, some other precession. There's like 4 different axes of it or whatever. And yeah. But yeah, they actually say that when they plot the minimum and maximum dimensions against the periodicity of the of that timeline for that precession to occur in the sky, they say that they get a match, which is really interesting. I think that there's like different ether velocities or different periodicities within the signal, but at that point they're at such a fine wavelength within the measurements. I mean, who really knows at that point? But that is an interesting aspect of what they pull out of closed loop interferometers, where they're allowed to have a variance, and so that's pretty cool. So does that kind of catch you up on interferometry and what's being measured and how it works? Oh, he lost connection. All right. So we're just we'll move on, and then we'll come back if you need any more clarification. Okay, cool. All right, so we did bombs, trains, Michelson-Morley, Sagneck, fictitious frames. We skipped a foreign pruner, but basically that was the Sagneck effect, where the source of light is fixed to the lab wall and the detector is also fixed to the lab wall. And they use 45-degree angled mirrors to hit a rotating platform and then bounce it back. And then that would create a fringe pattern proportional to the velocity that's measured as if the detector was on the rotating platform, but there's not, or, but it's obviously not, it's fixed to the wall. So relativity, predicting for inertial observers that the speed of light is constant, it predicts that there's no fringe pattern. And even if you invoke a fictitious frame to try and explain the results, that's actually off by an order of 10 or by a factor of 10. So it actually can't even explain de Four and Prunay. So that's another falsification of relativity theory. But we'll close out here on GPS and absolute time and relativity of simultaneity. So we went over the bomb and the train car explanation earlier. And it's like, where are there any practical explanation or examples of this happening? Because that's just a thought experiment. How can we replicate this in a meaningful way? Give me 1 second. I'm going to go to the bathroom real quick and grab some water. My throat's a little raspy. I've been recovering from being sick for all week. So if somebody wants to fill in or whatever, I'll be right back otherwise.
Yeah, this is Cassander. Can you hear me? Anyone?
Yeah, we got you, bro.
We can hear you. Go ahead.
Yeah, I've been taking some notes, And I came in when you were discussing Foley and Keating and their airplane trip around the world to test time dilation. One of the best references for that is Al Kelly's book. He really rips into H&K and all of the mistakes they made and their attempt to throw away some of the data. Anyway, if you want a complete story, see Al Kelly's book. Length contraction was discussed, and as far as I know, that's never been proven by experiment. What they do claim is that that they can apply time dilation, and then that proves length contraction. Well, what that really means is they're using the Lorentz transformation to do the time dilation, and then to piggyback on that and assume that that means there must have been a length contraction. So be very suspicious of any claim that says that they have proven length contraction. I'd be very suspicious of any experiment that claims that. On the MMX, of course, the big problem with the MMX was claiming that it was null. Null normally means 0. But what they actually measured was something, as Alan pointed out, that's about 6 or 7 kilometers per second. And it's even worse than that, because if you correct for the index of refraction of the interferometer's medium, you know there's different types of interferometers. You could have an air interferometer, you could have different types of gases, and you could have a vacuum interferometer. MMX used air as the medium. And if you use air, you come up with a corrected speed of about 360 kilometers per second, way beyond what they expected of 30 kilometers per second. So that's a correction to the MMX. Someone asked about ether resistance. Why do we have this resistance by the 20th century physicists to what almost every 19th century physicist believed in? Maxwell, Faraday, Hertz, all of the big names in physics in the 1900s believed that there was an ether, that there was a medium in which light traveled. The resistance of Einstein and all of the people who followed him in the 20th century, well, you might point to philosophical problems. They tried to assert the cosmological principle, like Carl Sagan, which says that the universe is the same in all directions. It's homogeneous, it's isotropic, etc. And the Copernican principle, which says that the Earth is nothing special, that it's just a speck in a huge universe. So there's a philosophical problem in asserting that there's something special about the Earth and the ether that surrounds it. So they want to get rid of the ether. And you could go even deeper and say, well, it's not just philosophical, it's religious. There's religious reasons for opposing anything that would support scripture. For example, geologists will never admit that there was a universal global flood, even though there's plenty of sediment evidence, layers of sediment that indicate that at one time the Earth was flooded everywhere at the same time by a huge flood. All the evidence is in the fossil record. and yet it's denied, usually by saying that there were local floods but not a global flood. That seems to me to be religious objections that are really underlying why they're objecting scientifically.
With this, I mean, how do you have a flood on a sphere, like inside an enclosed system, essentially? Where would all the supposed water be coming from?
Well, if you look at scripture, water was said to come up from the fountains of the deep, and also the rain is described as coming down in Noah's description from the ark.
Mm-hmm.
So the answer to your question is it came from two sources according to the Bible. It came from the heavens, and it came from the fountains of the deep, that is the oceans. Okay, let's look at relativity. Question there. Oh yeah, somebody asked, does Alan believe in relativity? My answer would be yes if you're talking about Galileo, and no if you're talking about Einstein. Galilean relativity is the basis for kinematics. And as long as you include ether as a possible source of the velocity that affects light, then Galilean relativity is valid. I totally reject Einstein relativity, and I'll be giving a talk soon on Einstein's train, and I'll be giving some substantial evidence to show why that the Galilean relativity is correct. The Sagnac effect was discussed. A diagram was shown which showed the platform rotating clockwise, but there was no diagram that showed the path of the light rays that go around the platform in opposite directions. And I think for a good understanding of the Sagnac effect, it's not just the rotation of the platform that you have to understand. You have to understand the effect of a dragged ether on light beams that go around the platform in opposite directions. A good model for the Sagnac effect would be, think of two runners, track runners, who have equal ability. So if they ran in a straight race, the race would be tied. They have equal talent. Send them around a circular track, running in opposite directions. If they have equal speed, they should reach the opposite side of the track at exactly the opposite side, the opposite diameter. But if there is what should I call it, a headwind, a vortex that boosts the speed of one and retards the speed of the other, then one will arrive at the halfway point before the other. Replace the runners by light beams and replace the air vortex by an ether vortex, and you have an explanation for the Sagnac effect. Liley asked about the tree and the train. Is the tree really at rest, or is the train at rest? Well, the answer is, if you make measurements, that is kinematics, then you can't tell. Either one can be used as the stationary frame of reference. But if you use dynamics, that is, you apply the laws of physics and ask how do objects move if the tree is stationary, which is the lab frame, or if you ask what happens if the train moves, which is the non-lab frame, then the answer is you only get correct answers for the laws of physics if you use the tree frame, the lab frame. So
How do you
as
figure in
usual,
kinematics? How do you figure this works in kinematics?
because it's only measurements. If you're on the crane, and you look at the tree, you take the train to be at rest. You see the tree moving. So you see the tree moving a certain distance at a certain time, and you say, well, it has a certain velocity, let's say north. If you're in the tree frame, you see the train moving south in the same at the same distance and the same time. That's the principle of simultaneity, which Alan just went through with the Einstein train.
Right, but
So
you'd
it
have to
doesn't matter.
believe that. Hold on, you'd have to believe that on a train that's moving, you have to convince yourself that it's not moving.
You don't have to convince yourself of anything. You just have to do the measurements. Measurements tell you, not your mind.
Well, maybe you, but okay, gotcha.
Okay, well, isn't this what science is, the scientific method? Doing experiments, making measurements? Okay.
Right, but I'm just making the point that you would have to convince yourself that you're on a moving train and you're not moving. That's all I'm saying. That's all I'm putting out there.
And all I'm saying is, if you make measurements, the measurements are the same except in different directions. In one case, the train is moving north. If you're measuring from the tree, and in the opposite direction, if you're measuring from the train. But if you apply the laws of physics, and I'm not going to get into that, I will on my presentation of Einstein's train, I will get into that, but the laws of physics will only be valid if you apply the laws of physics in the tree frame, the lab frame.
Shout out to the lab frame. Always making those correct predictions. Yo, real quick, Cass, while we got you here, you made an interesting point the other night regarding the lab frame and predictions in regards to measurements, in particular, like, for example, a pendulum. So they say, the Earth's rotation is what causes the pendulum to move. But isn't there some sort of kinetic energy analysis you can do to determine whether or not, which frame is moving and causing the motion?
You're referring to the Foucault pendulum.
Yes, sir.
True?
Yeah. Yes.
Yeah. Yeah, the vertical plane of the Foucault pendulum will rotate depending on latitude, and the explanation from an ether wind or a theorodynamic point of view is that the swing of the pendulum to the south, if you're in the northern hemisphere, will be hit by an ether wind that's slightly stronger than when the pendulum swings to the north. And so that causes, with each swing, a slight push, a slight rotation of the plane of oscillation of the pendulum.
Are you saying the pendulum?
I said the pendulum, what?
You're talking about a Foucault pendulum, right?
Yes.
Yeah, I think Alan is, yes.
Okay, are you saying, but the description, I'm just asking now, I'm not being confrontational. Are you saying that the pendulum deviates? Is that what you're trying to say? Because in the Foucault pendulum experiment, it's the Earth that rotates under, and the pendulum just moves back and forth. So I'm just asking clarifying question.
Okay, let me clarify that by asking you a question. Is that a kinematic or a dynamic statement? Measuring the rotation of a pendulum with respect to the Earth, and you're claiming that it's the Earth that rotates. How do you know that it's not the ether that is rotating, that's causing the pendulum, rather than the Earth? After all, that's kinematics, and that's relative motion.
Okay, so I get what you're saying. All right, so you're saying it's the ether that's causing the pendulum. Gotcha. And I'm not saying that I believe in the other explanation either. I just wanted clarification.
Sure,
Yeah.
that's the biggest distinction to be made is, are we talking about kinematics measurement, or are we talking about prediction of future motion using the laws of physics? If we make that distinction when we make these claims in the beginning, we can sort out what is true and what is false. And that's one of the problems that has to be addressed when we discuss special relativity.
So you were making
Because
a
claims that-
dynamic ref. Oh, sorry, I thought you were.
No, I was making a claim that you cannot tell whether it's the ether wind that's causing the pendulum to rotate, or the pendulum is fixed and the Earth is rotating underneath it. Because that's
Okay,
kinematic.
Yeah, yeah. But if you're saying it's the ether, then that would be a dynamic reference, correct?
Yeah, but you can prove that with dynamic arguments, yes. But you can't prove it with kinematic argument. No.
Okay, yeah. No, me, I have a big issue with the pendulum. Like, for example, have you ever seen two pendulums side by side do the same motion?
No, I've never seen
You're
that.
talking.
But real quick before we move on to the anomalous pendulum behavior, Bennett, wasn't there an analysis you can do similar to Bennett's hiker, where you know only the stationary Earth makes the correct prediction for the force applied to the pendulum? So I think that's a really important argument that's been underused and never really represented.
You know, I haven't analyzed the Foucault pendulum dynamically. I guess you could use energy considerations, right? You have the kinetic energy of the pendulum.
Yep.
Exchanging energy with the potential energy, right? As you have a pendulum swinging back and forth, when it stops at the top of each swing, its kinetic energy is zero, but its potential energy is maximum. And then when it's at the bottom of the swing, its kinetic energy is greatest, potential is lowest. And I'd have to work that out, Alan. But yeah, I think with the Foucault pendulum, you could work out something similar to the hiker or the Newton's bucket or any of the other ones.
Or the biker. I like the biker one too.
Yeah, in fact, you can use any non-lab frame as an example of something in which the laws of physics are not obeyed. It's only the lab frame in which the laws of physics are valid. If some of you are wondering what we're talking about, there's a theory I have called alpha, in which you can show that in dynamics that there's an absolute lab frame, which means the Earth is the only frame in which the laws of physics are obeyed. And the other part of that, the FA, means fluid ether, which means that the explanation of the laws of physics a lab frame depend on the concept of a fluid ether, an ether drag, if you will. Every moving object drags ether along with it relative to the Earth.
Would you say in your conception, I kind of want to also plug in SE's statement a little bit here, of the like having two pendulums performing the same action side by side would be very interesting, because then it gets down to the point of like, do you think in your concept, can we actually build or manufacture a product, a join, which is so, how would you say, like symmetrical and perfect, such that we're picking these this effective Coriolis or the ether wind up?
Well,
Like,
I'm not,
yes.
I'm not following why you need two pendulum. What pendula?
Okay. Okay,
If
because
you
the
have
conception is
Penduli, they call
for the
them.
reason like all of these pendulums seem to have some form of active motor inside of them to keep them going back and forward. So the designs sort of actually require some form of manipulation at that point. The reason for having two side by side is to see whether or not they corroborate one another, because just to cut to the quick of it, essentially it would be my interpretation that if it's not the mechanism basically performing and forcing the rotation in and of itself, they may manufacture sort of these joins from where the pendulum connects to, and they wait to see if it processes, and then what is it? Essentially, however much it processes around, then they would just go deliver that particular pendulum to a certain place on Earth in order for it to corroborate the claim of Coriolis effect.
Have you ever seen a Foucault pendulum?
Yes, I have. It was not at the time now that I have much more of a focus and to attention. I'd be looking at it a little bit closely, but I've certainly seen one when I walked through a museum, several years ago.
And did they have a mechanical connection to it that kept it oscillating, or was it free swinging?
Specifically, I'm not sure about the one I saw, but it is my understanding that most of the ones, if not all of them, in museums are essentially mechanized.
Well, that's not my understanding. What usually happens is, in order to get a release of the pendulum with its motion at zero, there's usually an electromagnet that connects to the ball, to the pendulum, and holds it fixed, so that when you cut the power to the electromagnet, the magnetic field collapses and the ball is released. That's the only mechanical connection that I know, or the only way of adding energy to the pendulum. The way it loses energy is air friction. As it swings back and forth, it loses energy to air friction, so eventually the pendulum will stop. It takes a long time.
It would lose energy also inside of the friction caused inside of the joint, which gets to the point of, in your interpretation, do you think that we are actually capable of producing such a perfect piece of machining, such that it's actually, how would you say, like in and of itself, it does not have any inclination to go left or right or perform any precession? I just think that would be a very remarkable feat in engineering to do that, with the tolerances required to achieve it, to manufacture that. Do you get where I'm kind of pointing at there?
I think we have we have a different concept of the pendulum.
Well,
The
if I can add
operation.
something before you go too much further,
Yeah.
the pendulum it does have, a lot of them have cool ways, and I think magnetism is used in this also when I researched it, but they don't help it process like in a certain direction, but they help it stay in motion so it does process. Does that make sense?
Yes, that makes sense.
But that's where the
To compensate
mechanical
for air friction. Yeah.
right, they know it's going to stop eventually because of the reduction in energy, just friction alone, right? Air friction, but they keep it going with these mechanisms, and people have kind of insinuated that they can control the direction, but I'm not insinuating that. But they do keep them swinging back and forth at a certain rate by using a mechanical mechanism attached to the ball joint, and I believe it's magnetism that they use.
The installation manual actually it talks about how you calibrate to get the expected result. So,
Oh no. So
I mean,
yeah.
somebody
So
here's got the PDF, but this is for demonstration purposes, not the scientific one that Cassandra's talking about.
yeah.
Well,
So
to be
this.
honest, the calibration, I'm not like, I'm on the side of, I'm not sure what a pendulum, how it processes, but the calibration could be just the distance and rate that it swings back and forth. The precession, I'm not so sure is what they're talking about, but you might know more about it than I do.
I just don't understand how you could actually produce that in the physical world, given like the tolerances that would be required. Like it's finer than any engine we've ever produced.
Cool.
Yeah. I mean,
So yeah, there's some
going for
ambiguity
whatever
in the
reason.
measurement there. So whatever. Doesn't matter. Anyway. Thanks for taking over for a minute there, Bennett. Much appreciated. But we're gonna.
Yeah, Alan,
Go ahead.
we have to talk about the Einstein train. Do
Oh.
a voice chat tomorrow or something.
Oh,
Or I'll
absolutely.
send you email.
Yeah, absolutely. Anytime that
Yeah.
works for you works for me.
I've got all of the document done, except I want to do audio editing with Audacity,
Nice.
which is a software product that was recommended. I'm just starting to use that.
Nice.
But glad to hear that you're feeling better. You sound better.
Thank you.
So we'll talk next week about setting up some time for the
Awesome.
presentation.
Nice. Looking forward to it.
Okay. It's
Heading
almost
off.
1. I gotta
Heading off.
go. I need
Later.
Thank you,
need my
Dr.
beauty. Yeah. Take care.
Peace. All right. So to close out on GPS, we were talking about how the speed of light has to be constant in all frames, et cetera, can't be measured differently, yada, yada, right? Well, when we get into GPS, how does GPS determine the velocity of the observer? The GPS system uses a range measurement equation, which derives distances based off of when the time the signal was sent, time minus the time the signal was received, times the speed of light, which gives them the distance that had to have traveled for them to get the signal from when it was sent and received. So from that, they say, the speed of light's constant and blah, 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 doesn't require any sort of corrections or anything like that. But this equation that's used specifically can be used to derive the Sagnac effect, which we talked about earlier, and how it's a first order effect. It requires the measurement to be made with respect to absolute time and space. Otherwise, it's not going to be accurate. And what they actually say here, when you go through the ICD documents, which is the interface control documents for GPS, I have the 2010 edition here, and they kind of changed the verbiage in the later editions because it's pretty obvious when you read it. But anyway, what they're saying here is that there's a Doppler shift in the light that's measured by the receiver, and that's what's helping derive the velocity. And if that's true, then one, you can distinguish inertial frames from being stationary versus being a uniform motion with Doppler shift. And it's not possible for there to be a Doppler frequency shift without the speed changing, because that's what creates the change in the wavefront is what creates the variance in the measurement for there to be an effect, because the wavelength and the frequency have to change inversely proportional to one another. So if there's a frequency shift, there has to be a wavelength shift as well, which changes the wavefront, which is going to change the speed of light. So this is like a tacit agreement that the speed of light varies irrespective of the velocity, or I'm sorry, it varies with respect to the velocity of the observer. And it doesn't work in the way that Einstein proposed. This is extremely significant because GPS doesn't care if you're traveling in a straight line or running around a racetrack. It's going to give you a timing difference proportional to your velocity that's going to allow your exact position to be triangulated through trilateration, through other signals being, intersecting you at that point. And further, right? So GPS works on trilateration, so signals being sent to observers from different stations or different, satellites. So what you can interpret from that is that suppose you have two satellites or two GPS stations that are emitting signals, and because it's GPS, it's all synchronized to GPS time. If you're using GPS, you're using GPS time, which is an absolute timeline that's broken down to 9,192,000,000ths of a second. And from that, you're using this absolute timeline, and you have signals being emitted in synchronous events with respect to this absolute timeline. And so you have observers that are getting their signals from these satellites. Now, suppose you have two satellites that are emitting their signals at the same time, and you have observers in a moving train with respect to a stationary platform. This happens thousands of, millions of times a day throughout the history of GPS since its inception. And never once has there had to be a relativity of simultaneity correction, because remember, the synchronous of events is determinant upon your velocity. So if you're moving closer to one of the satellites and away from the other one, there should be a timing difference in the time that the signal was sent in which you received it. And you would have to do a Lorentz transformation to, figure out the difference and all that. No one has ever used a Lorentz transformation in GPS. It all works off of absolute time in between the ECI and ECI reference frame. They do Galilean transformations, which is in reference to absolute time and absolute space. And the range measurement equation itself basically accounts for a variance in the speed of light proportional to the velocity, which is how they get their timing difference. And they attribute this to a Doppler shift in the receiver. But obviously it's a little bit more than that, than just a shift with respect to somehow a constant velocity wave, because the timing difference matches as well. So it shows that the velocity of light is measured c plus or minus v with respect to the observer moving towards or away from the light source. And that is, go ahead.
Oh, go ahead.
I was just going to close out and say that's one of the biggest falsifications of relativity theory that's available. Because a lot of people will say, you can find pop sci articles that are like, relativity is proof of GPS is proof of relativity, and we have to do all these relativistic corrections. They only account for the Sagnac effect in the GPS clocks. They make routine meridian corrections as the satellites carrying the clocks past GPS stations. So they're constantly deleting time to make it compatible with how long it would take to fit the coordinate system and the altitudes that they're using it. And with all of that, it just doesn't.
Wait, so GPS receivers just get position, not speed, right?
No, they give you a distance based off of your speed, which comes from a timing delay in the signal sent.
I don't think that's right.
They use a range measurement equation with respect to the GPS timeline. The range measurement equation is the time the signal is sent and the time the signal is received times the speed of light, which gives them a distance. That distance will be is accurate down to the millimeter, and if you're moving, it's still accurate. And the reason that it accurately derives your distance is because you receive the signal varied with respect to your velocity, directly proportional.
Yeah, the guy who actually fixed GPS, like it didn't work good before, and now it works way better. Like, you know, you get to a tighter range. The guy who fixed it was responsible for that. Actually wrote a book called Escaping Einstein. I think his name was Ron Patch, maybe. But you're saying the simultaneity bomb on the train thing, you're saying that because you just replaced the lightning bolts with the
Oh yeah.
GPS signals.
Yep, exactly.
And
Yep. If you
you're
replace, yeah, sorry, go ahead.
Yo, that's crazy. Go ahead.
Yeah. Yeah, no, yeah, you nailed it. That's the connection, right? So if relativity of simultaneity is true, if you were going to keep everything synchronized with respect to an absolute timeline, you would have to make relativistic transformations to facilitate that, and they don't do that. They explicitly use Galilean transformations, which are absolute. And real quick, we'll end on this paper here from 1996, sorry. This is an engineering overview for relativity and GPS, because in 1979, there was a guy named Professor Carroll Alley who did an experiment with atomic clocks similar to what Heffel and Keating did. And he went on this big announcement and was like, relativity is no longer just a make-believe thing. It requires, it's a necessity of engineering now. Now, it's a really big claim, right? Because of this experimental evidence, he said that, confirmed relativity theory. And then they ended up, never doing that. And this guy, worked heavily in GPS on the back end for the coding and all that, building the infrastructure of it. So we'll get to a later comment from him. But in 1996, there was an engineering overview that was put out, because all these engineers were like, hey, we heard relativity's in GPS, but like, where is it? We've been looking for it, where to put it, and we can't find it or whatever. Right. And so what the purpose here is, because we've all heard that GPS has to make a correction for the general theory for gravitational redshift, for the difference in potential for the clock at altitude, and then what's the other one they make? Time dilation, which is basically them saying, yeah, it's like an Earth rotation correction for them essentially, but they treat it as a time dilation effect. So they account for those two. And they're like, but actually, those two effects cancel each other out, and we don't need to account for them. So in this paper, he goes over the math for the effects and the magnitude that they come out at, which is, what is it? It's like 32 microseconds and then 27 microseconds or whatever. So it's just, they're like, well, we don't even need to do anything because they cancel each other out. So, and then at the end of that paper, there's a segment by this gentleman right here, our boy Carroll Alley again. Oh, shoot. 1 second. Let me get the proper Carroll Alley thing. My apologies. So here's Carroll Alley in that same paper. At the end, he's like, hey, I think we should include special relativistic effects. It took a long time for us to figure out how to get the general theory in there. And it's a real shame that there's no relativistic effects in there due to the consequences of the relativity of simultaneity and the associated Lorentz transformations. So, changing time and distance axes and making corrections for events not being synchronous with respect to velocity and all these things. And he's like, maybe we should include those. They've never included those ever. In fact, Neil Ashby in the 2000s was telling people that the Sagnac effect is proof of Earth rotation, which, we're scooping up as ether rotation. But in the transformations, he goes over what they use for the ECI and ECF frames, and they use T prime equals T, which is just Galilean transformations. There's no changing time as a function of velocity squared over c squared or anything like that. They're using absolute time and space for GPS, and it's synced to a absolute timeline as well. So, which is antithetical to relativity theory.
Good stuff, sir. Good stuff.
Thank you, sir. So yeah, factually falsified, by experiment and by measurement, right? Because maybe you want to argue, well, GPS isn't an experiment, et cetera, or whatever. It's okay, fine. But this measurement shouldn't work the way it does without the corresponding mathematical transformations to give physical meaningfulness to what's proposed in the mainstream paradigm. And the fact that it works with classical equations and a variance in the speed of light, shows that the interpretation of relativity isn't the correct interpretation because it's making the physical wrong prediction here.
So the one thing they point to satellites, oh, we knew it was like a joke, but now, you just put a nail in it, bro. Well done.
Yeah, thank you, sir. But yeah, they've never changed those. And then there's a really interesting thing you can do, which I don't remember the full details off the top of my head, but we came across that that correction they have for the gravitational potential difference, the way it comes out. You can derive that difference from the Sagnac effect. So if you have an orbital diameter around the Earth at, whatever altitude, but as long as the diameter over top of us in a circle or circuit is 20 kilometers, everything they're doing would scale as if it was a ball and they were at 20 kilometers in altitude, the way the differencing would work. I have to get Pizio to run me through how all that would work again. But basically, the way that it would be scaled so that they could have the timing offsets so that it would all appear proportional to a satellite in orbit at 20,000 feet versus closer, just moving at a different velocity, would be scaled through that set function that they have for those values that they give for relativity that supposedly just cancels out, so they ignore it. So there's even a further connection there that we could take it.
Well, they can't have it both ways, right? They can't say it's this and then not include it in their calculation. So,
right.
I mean,
right.
Yeah.
They absolutely can't. They absolutely can't. Well, I am fresh out of material and I've been going for a hot minute, but I don't want to hold the room hostage or whatever. But after Mordwan finishes debate, or he's doing the after show now or whatever, I'll probably need a break. But we were planning on picking up the conversation with Miller's work and the Sagnac effect. So if we could return to that later tonight, when the conversation dies down or whatever's going on later, we'd like to return to that. But I'm going to go ahead and wrap up now, since I don't know when he's going to be available, and I don't want to, after a debate, you don't want to be like drawn into another long event or whatever. So anyway, I'm going to wrap up now, unless there's any further questions or anything like that for clarification. Otherwise, I'm just going to go ahead and end, and then we could get back to the rest of our night, gentlemen. I thank you all for listening to that presentation and going through it all with me. I hope it was insightful. And if you have any questions, please feel free to ask.
Good stuff. Good stuff.
All right, lads, I'm wrapping it up. I'll be back in a couple of minutes. Yo, lads and ladettes, thanks for holding it down in the chat. Much appreciated, everyone. We go through, see who showed up tonight. We got our boy Shane, Ether Dynamies, all one word. Got Joanne, Truth, the boys Hercules, Maria Walker, Logical Observation, some guy named Raj that got super banned. I think I see my boy Bogan, Jason E, all the lads, Eric, Yoshi, Crash, Dr. Bass Ackwards, dude. Shout out to the lads. Catch you guys on Tuesday. I'm going to be doing a presentation on the Sagnac effect. Dude, we get to do it all again, boys. So I'll have a nice refined Prezi for the Sagnac effect. For the Sagnac effect and the measurements and all that. For Tuesday, we'll go over that. And then Thursday will be research and reading night. And then Friday will be Flat Earth Fridays, episode 119. If you're not familiar, there's a Twitter thread for potential topics for next week. So if you want a specific subject to be talked about next week, put in a vote for that on Twitter. You can find that on Proud's Twitter. Her Twitter handle is @LevelheadsHQ. That's Levelheads with a Z. All right, lads, I'm heading out, and ladettes, catch you guys on Tuesday.